Good evening, everyone. It is a great honor and privilege to welcome you all to today's event. We are gathered here to learn, exchange ideas, and be inspired by an exceptional professionals who have made remarkable contribution to the field of engineering. We are delighted to have with us Mr. Arun Shankar VK, a distinguished engineer, researcher, and innovator, currently working as a senior software automation testing engineer, specializing in hardware in loop at Danfoss Industries USA. We welcome you, sir. Also welcome all the faculties and facilitators who are here to attend this session today. Now, I welcome Dr. Lijo Jacob Verghese, Head of Department of Electrical and Electronics Engineering, Sri Krishna College of Technology, to deliver the inaugural address.
Good evening, a very warm evening to all the distinguished participants who have joined here in the Zoom platform. As I welcome you, each of you who have connected to attend the AICT Training and Learning Academy, ATL-sponsored one-week faculty development program on the next generation and smart grids for sustainable power systems, the path from Industry 4.0 to 5.0, which begins today and extends till the 7th of December 2024. I'm positive that this FTP would be a great platform to help all the participants to draw inspiration for their research and would help them in the advancements of their quest for the search in the innovations in sustainable energy applications. This event is a fruit of the joint venture made by the Department of Electrical and Electronics Engineering, Sri Krishna College of Technology, Coimbatore, in association with the All India Council for Technical Education. Sri Krishna College of Technology was established in the year 1985 and is promoted by Sri Krishna Institutions, Coimbatore. In the span of 39 years, the college has emerged as one of the premier engineering colleges in imparting holistic education as a center of learning, discovery, research, and innovation. The Department of Electrical and Electronics was introduced in the year 2000, and the postgraduate program on ME Power Systems Engineering was initiated in the year 2013, along with the PhD program in the core electrical engineering specializations. At this juncture, I would like to take this time to thank our source of encouragement and a pillar of support, our revered chairperson and managing trustee, Srimati S. Malavari, for the display of dynamic leadership and support for empowering us with all the needful resources for conducting this event. A special thanks to our young and dynamic trustee, sir, Sri K. Aditya, and Dr. K. Sundararaman, the Chief Executive Officer of Sri Krishna Institutions, Coimbatore, for all their support rendered. I would welcome our respected principal, Dr. N.G. Sumitra, for all her insights and inspirations in organizing an FTP of this stature, and indebted to wholeheartedly welcome all the heads and faculty of the various departments and thank them all for their varied and valuable contribution. We'll be having a distinguished academic and eminent industry delegates who would be enlightening us in the course of this week, touching upon the various aspects of innovations in sustainable energy and smart power systems. On our inaugural session of this FTP, it is a matter of pride that we have with us an eminent personality to empower us with this topic, an industrial expert, a man who had done so much research in this field, Mr. V.K. Arun Shankar, the Senior Engineer, Automation Testing, Danfoss Industries, Loves Park, USA, who has gladly consented to give a session on this topic. And the session will also be enlightened later this evening by an academic expert, Dr. K. Vijayakumar, Professor, Triple ITDM, Kanjipuram. On behalf of the management, faculty, and students of Sri Krishna College of Technology, I wholeheartedly welcome you, sir. It is my honor to welcome all the heads and the faculty members of various departments of SKCT and sister institutions who accepted our invitation and joined us to be a part of this event. I would welcome and congratulate the faculty coordinators of this event, Dr. S. Jayashiva and Dr. S. Dilip Kumar and their team, and thank them for their varied contributions. My task would be incomplete if I fail to welcome all our dear participants from the academia and industry who have joined this FTP. I'm sure that this FTP would offer a forum and useful in providing vast academic resources, as I wish and hope that the deliberation in store for this week would definitely bring a rich learning experience to each of you who have joined here this platform. I also extend my heartiest welcome to all the faculty and the student volunteers of the EEE department who work behind the scenes for realizing this event in reality. Once again, on behalf of the management, faculty, and students, I welcome one and all. Thank you.
Thank you, sir. Now I welcome Dr. S. Jayasiva to deliver a few words about this FDP.
Good evening to all. A warm greetings from Department of Electrical and Electronics Engineering, Sri Krishna College of Technology, Coimbatore. I welcome you all to the AICT Atal sponsored 6 days online faculty development training program on the topic of next generation smart grids for sustainable power system, the path from Industry 4.0 to 5.0. This program is being scheduled between the dates of 2/12/2024 and will be completing on the date of 7/12/2024. And this program has been structured in line with the guidelines given by the ATAL. The total number of participants registered for this event is about 150 participants, which includes research scholars, academicians, and industry persons in and around all over the countries. The main objective of this FDP program is to provide recent and advanced approaches for next generation smart grids to develop a sustainable power system, which will offer a pathway for the industry 4.0 to 5.0. The various topics which are to be covered in this FDP programs are advanced IoT solution for smart grid monitoring and control, a role of smart grids in sustainable energy management systems, integrating circular economy principles in the power systems, cyber physical systems in power systems engineering, and future of smart grids beyond the automations. And along with this, the introduction to Industry 4.0 to 5.0, a power system perspective, and integration of renewable energy sources within the smart grid for the future development of a grid network, designing resilient power system for future industries, policy makings and regulations for sustainable smart grids. And I hope this faculty development training program sessions will gain you a fruitful knowledge towards the advancement of all your careers. And let's all get benefited by this AICTE sponsored Atal faculty development training program. Thank you all for joining this session. And I now welcome Mr. V.K. Arun Shankar to have a session on this IoT sponsored advanced IoT solution for smart grid monitoring and control. Thank you all.
Thank you, sir. It is my privilege to introduce our esteemed guest, Mr. Arun Shankar VK, whose exceptional academic and professional journey serves as a source of inspiration. He completed his undergraduate degree in electrical engineering in 2012. He further pursued his master's in power electronics and drives at Vellore Institute of Technology, Chennai, and graduated in 2014. Demonstrating a commitment to blending academic excellence with industrial innovation, he undertook a collaborative PhD sponsored by Danfoss Industry, Denmark, on the topic Energy Optimal Staging and Destaging of Cascade Centrifugal Pumping Systems for Performance Enhancement at VIT. Currently, he is making significant strides as a senior software automation testing engineer specializing in hardware in loop at Danfoss Industries in Loves Park, USA. His expertise spans diverse areas, including HIL, model-based design, electric drives, energy efficiency for centrifugal pumps, and machine learning. With over 30 international journal and conference publications to his credit, Mr. Arun Shankar has established himself as a thought leader in his domain. He also contributes as a reviewer for prestigious journals like Elsevier and IEEE Transactions, a role he had held since 2015. We are indeed fortunate to have him here with us today to share his knowledge and experience. Let us give him a warm welcome and eagerly look forward to his presentation. Over to you, sir.
Yep. Thank you for the warm welcome. I hope my audio is clear and then you can able to hear you guys. Can anyone acknowledge that?
Yes, sir. Your audio is clear.
Thank you. Thank you so much, sir. And
thank
I'm very honored to be a part of this session. And thank you, Lijo, sir, for your warm welcome. And that was really a good speech. And yeah, so I'll proceed to my presentation. I hope you can able to see my screen. Let me know if you're not able to see it. Can you guys able to see my screen?
Yes, sir.
Okay, thank you, sir. Thank you so much. Yep. So yeah, like I said, it's really my honor and my pleasure to be part of this 6 days faculty development program. And today I'll be presenting more on the topic related to the IoT solutions for the smart grid monitoring and control. So since I work for a company called Danfoss, so it will be like they will be manufacturing electric drives. I'll be going through what we are actually into, what we manufacture, and how we are related to the electric grid, and what are the things we manufacture for altering the grid parameters. So all these things I'll go through in a brief way. So I'll be very happy in case if you guys have any questions, I'll be very happy to answer them. If I were not able to get some answers, I'll be very happy to get you guys from my colleagues or whoever is working on that concerned department. So feel free to be as an interactive session. I'll be very happy for that. So yeah, I think we can go ahead on this one. Yeah. So today, mostly I'm planning to present on few topics. That is like, what are the energy efficiency challenges that we are facing in industry as well as in the commercial world, and what are the testing that we do it actually as an industrial drive. So I'll showcase how the industrial drive testing will be happening in industry point of view, and in case what are the harmonic distortion we got it. So when we test some power electronic equipments, right? So of course we disturb some parameters in the grid, and we have some harmonic distortions, like we disturb the grid parameters, and how are we going to rectify them, and what is the current trend in electrical testing actually. So how we are going to test the electric grid or the industrial electric drives, what are the current trends actually. So when I talk about the current trends, so hope you guys already have come across some of the hardware in loop concepts, like hardware in loop or software in loop or control in loop. So I'll touch base a lot of them actually, so how they are actually helping us on all the testing point of view, as well as how they are reducing our cost when we are trying to build any product actually. So I will compare the conventional method of creating a product, starting from scratch, from a simulation or to going to the hardware and to the testing, and to the current trend actually. So compared to the conventional one, how we are actually different in the current trend by including the hardware and loop concept on any product. So I'll showcase on the electric converter or the motor, how we are doing it. And finally, I can showcase some of the research opportunities. If in case some research budding engineers, they are in their beginning phase of their research, let's say if they have started their research or planning to start their research, or if they want to pursue their postdoc or something like that. So I have some of the points which I have come across, or from end of my research, I have some points actually. So I can share them. So if you guys are, feel free to take up on that, start working. I'll be very happy, and then I can also support in case if you need. But you guys are feel free to work on those topics. Actually, those are some of the research outcomes after my completion of my doctorate, right? So I was able to see that these are the open areas that are left actually. So if someone can start work on that, there are a lot of industrial openings actually. Those are things are available. So yeah, with that note, I'll start. What is Danfoss in brief, actually? So yes, I do have a good relationship with SKCT. So we have been delivering a lot of lectures, and I have some good friends working there. And then it's been really a very good pleasure actually. So to be part of with SKCT, and some friends, if they were new to Danfoss, what is Danfoss? Sorry. So Danfoss is a company. We were into like three main domains actually. One is like power solutions, another one is the climate solutions, another one is power electronics and drives. So on an electrical point of view, we were mainly into the power electronics and drives, which means we manufacture a variable frequency drive, which can control the speed of an electric motor. So when I talk about an electric motor, it says like industrial workhorse, that is a induction machine, and the high power, high efficiency machines like permanent magnet machines, and also the recent trending machines like synchronous reluctance machine. So these are the major three machines we are working. Apart from that, we also support for other kind of machines like one drive machines or stepper motors, all these things also based on the application, whichever the customer needs. So we also support for them. And out of these power electronics and drives, we also have climate solutions where we support for other countries like where we have the cold regions, right? So we have to provide the heating and ventilation uh, for them. So for that, we need to provide heating concepts where we produce some compressors, compressor valves, all these stuffs actually for them. We also provide a complete climate solutions, HVAC. So for that also, we still have a drive. So with which we'll measure what is the temperature of the ambient, and then based on that, the compressor or the whichever the heating element, right, that will be run, and then that will be compensate the heat gap between the current value and the set value. So that is for the climate solution part. And coming to the power solutions, there are a lot of off-road vehicles actually. So some of them we are able to support them for the EMC unit, and for the other electric related stuff, we are actually converting from the normal conventional fuel to the electric fuel. So not only on the normal conventional cars or bikes, we are also moving towards the off-road vehicles. So like marine vehicles and mining vehicles, ships, ferries, all these things, right? So for all these things, we are also still trying to migrate from the conventional fuel to the electric fuel. So for them, how we are actually supporting. So in Danfoss, like I said, so we also have a unit called Editron, so which they completely manufacture the variable frequency drives or the inverters, especially for the electric drives compatibility. So that is what about in brief about Danfoss. So like I said, we were actually in Europe is the headquarters, like Denmark is the headquarters of Danfoss, so which holds around some 40% of the global economy, and 22% in Asia, like in India and China. And coming to the US, we have it in Laos Park, that is in near Chicago. So, and another one is from Tallahassee, it's in Florida. So these are the few major key places we are into. And these are the employee counts, and these are the global footprints, what we have it. And the main focus about Danfoss is like we are focusing about reducing the carbon footprint. That's the main focus. So moving towards as much as possible, we are reducing the carbon imprint in the society, and then we are trying to improve the efficiency of the product that we are manufacturing, that is electric drives or compressor valves, whatever it is. So yeah, so that's all overall about the Danfoss. Then I'll show you, these are some of the locations, like I mentioned, North America, Latin America, and we have the North Europe. So coming to the India, so we have an office in Chennai where we have a production unit, everything. And we also have some of the sales offices in the Middle East and Turkey and Africa. And currently we acquired a Semicron, which is like not currently, like couple of years back. And then you guys may be knowing the Semicron is like kind of they are a manufacturer of the power electronic switches, your IGBTs, MOSFETs, all these things, rectifiers, everything they manufacture from the Semicron. So we have a unit in Germany. So yeah, that's all a brief intro about Danfoss things. And for whoever people they worked on variable frequency drives, this is how it will be looking like. So you have a variable frequency drive that will be driving a machine. The output of the variable frequency drive will be driving the machine, and the input will be connected to the grid, so which we are more concerned about. So the grid will be supplying us the fixed voltage and fixed frequency. Either it can be India or it can be US. So whatever it is, 50 or 60 hertz. So that will be a fixed input frequency to the variable frequency drive. From there, we will be running our control algorithms and then power electronic switches. Based on that, we'll be trying to switch on or switch off the control logics, and then we'll be running the application. I mean, in the generalized way, application in the sense. So here I have shown a compressor application. So my research topic was on pumps. So likewise, different applications or different customers, they have different needs. So based on that, the motor is going to be the same. So from that motor, that is going to drive the end application. It can be compressor, pumps, or blowers, whatever it is. So likewise, so a frequency drive or a variable frequency drive, what I mean is just going to speed control of an electric machine, which will in turn control the speed of any other application that we are connected to it. So you guys might have a question, why do we need a variable frequency drives? And in case if we have a lot of disturbance in the grid, and what are the other solutions we have it? So I have answers for all your questions in the upcoming slides. So before going to that, these are some of the products that were into the market. Like we have some markets drives like micro drive, MIDI drive. So these micro drive and MIDI drive are for kind of a very small applications, like kind of a 0.45 kilowatt, starting from 0.45 kilowatt. We still have up to 2 megawatts drives supporting. So if you can see here, so these are some of the panel drives which we can build it, and that can go up to 2 megawatt drives as well. So when it comes to an application drives, like what I mean application drive is, so if you see here, the automation drive, Aqua drive, and HVAC drive, all these three drives are actually by hardware, they are the same. So just by the application, let's say if the customer needs a drive for a pumping application, so we go for an Aqua drive, so which actually controls an electric motor. So that in turn controls an pump, or it's a centrifugal pump, or it can be a reciprocating pump, whatever it is. So it will control in terms of a pump. So when it comes to automation drive, it will control a automation related stuffs, like you have a conveyor belts, all these things. So, and similar way for your HVAC, it will control the heating, ventilation, and air conditioning unit, like it can be a compressors or all these things. So you can ask me, what is the difference then it makes? So by the hardware, all remains the same. But when it comes to the software, so we have a dedicated software for each of those drives, which can take the inputs. Like if it's a Aqua drive, it will take the flow rate as an input. So it will control or maintain the flow rate. And it comes to the automation drive, it will take the position as the input. So based on that, the conveyor belts or the bottle filling, all these things could be much more easier. And similar way it comes to the HVAC. So likewise, we all have all these things. And finally, the important topic is on the low harmonic drive actually. So in case we have a real drive, so which actually tries to run the real drive, and it is producing a high harmonic values. So we have also the low harmonic drives, which can add up in parallel to the real drive. So that will reduce the harmonic on the grid point of view. And also we have the advanced harmonic filters actually. So those are the concepts that we come up for reducing the grid pollutant. So we can make better grid, even though if we need high efficient drives for our application. So that's why we have all these advanced active filters and harmonic filters. Those are really to make the grid more stable. So apart from the drives that Danfoss is manufacturing, Danfoss is having a second umbrella called Vacon. So we also manufacture the similar kind of drives actually. So all the drives, like I mentioned in the industrial flow and what is it? Yeah. So industrial Vacon and air cooled. So all these three things are the analogy of what I mentioned. There is an automation drive, Aqua drive, and the HVAC drive. So here, the best part is about the air cooled drive. So we also have a water cooled drives. So if you see here, it's a liquid cooled drive. So when we are using for a compressor application, so we also have a liquid cooled drives where the water from the compressors, anyway, the compressor is going to use the water as a refrigerant. So from there, those water can be used for cooling the power module, which is available in our electric drive. So that's why we have it as a liquid cooled drive. So that's one of the different technology what we have it under the Vacon umbrella. That's why I wanted to show it. Yeah, still we also have like a NXP grid converter, and we have a low harmonics that we are going to discuss more. So like that we have it. Yeah. So coming to the energy efficiency or the energy consumption. So this is the graph, or like we have a growing energy from 1980 or before that, and it will continue to extend actually. So currently we were in like 2024 or 2025 entering. So when you see that next 5 years also, we are still going to need a lot of energy. So either it's our responsibility as an electrical engineers or the people who are working on the electrical side, it's our responsibility to come up with some novel techniques, either to limit the energy consumption or to produce enormous energy, a clean energy, I mean. So which we are able to feed the energy demand, what is available in the globally. And we should be able to be producing an energy that is more efficient than before. So because when the population goes on increase, of course, the energy demand goes on increasing. So we should come up with some kind of more energy efficient technique. So to produce the clean energy on the grid point of view, and also on point of view of the electrical equipment that we are going to run it. So it can be an electric drive or machine or pumps, whatever it is. So we should not pollute them, and also we should not pollute the grid also in turn. So that's the main focus. All the electrical engineers will start our career, like our doctorate or something like that. So from there, so we'll think about what is the best way to produce energy. So then people dive into the renewable energy sources like solar, you have a wind, and now people recently started working on the fuel cells, hydrogen, and so lot of things. We have a lot of open research areas that is available now. So to mainly focus on the main objective, if you ask me, like almost all the research that is being carried out in the electrical domain started with the point called energy. So we were mainly focusing on either it can be an energy improvement or energy consumption reduction. So whatever it is, so mainly our focus will be like concentrating on the energy. So I would say this is the starting point for most of our researchers. So from there, if you ask me like how the energy efficiency could be improved, so for all the research area, just for time being, you don't consider the third level of classification, but in the second level of classification, so if you consider all the topics or all the research areas in electrical engineering, so we have only 3 divisions actually. So for improving energy efficiency in any system, it can be anything. It can be a drives, it can be a power system, it can be a power electronics. So whatever the area it can be, for improving energy efficiency or enhancement of that particular system could be done only on the major 3 ways actually. Either you select the components in a better efficient way, whichever the system that you're working on, or second thing is like you're properly dimensioning that component actually. So I mean the system dimensioning is like, let's say if the system that you're going to design is, let's say, 10 kilowatts or something like that. So how well you are defining that system. So whether you are under defining or over dimensioning, so that makes a lot of difference in the energy efficiency of that particular system. So some people, they might think like we need to over design the system so that in the future if we might need it, right? So we can able to run it for the higher size also. So that's not a bad thing, but a proper planning has to be made. So because like when you design a system for the over sized, right? So then you're not operating that in a full load efficiency. So then of course the efficiency you might get will be much lesser when compared to running that system in a full load. So a proper system dimensioning is very important when coming to considering any system. It can be from starting from the grid to the end user application. I mean for a pump or compressors or whatever it is. So starting from the grid to that particular end application, the proper system dimensioning is very important. And third one is the control and adjustment. Sorry. So the third one is the control adjustment. So when it comes to, like I said, in our case, I'll be talking more on the electric drive system. So in this system, so you have an electric control systems like variable frequency drive, VVF, or most of the people would have heard on the topic like a scalar and vector. And from in the scalar, we have a VBF control. In the vector, you have a FOC control, DTC control. So all these things are called as the control algorithms for switching on and off our drives, right? So in that case, so how well our control algorithm is going to operate. So whether it is going to produce more amount of harmonics in the grid, or whether it is going to have a precise control on the output side, whether we are going to have a good efficiency on the machines. So that's what is all about important actually. So we need to trade between all these factors. So whether if a country, so we cannot able to sell the same drive in all the countries, right? So every country has its own regulations. Like some countries, they expect the drive to qualify for a UL certification or for an IEC certification. So each certification will have its own grid permissible values. So if you see like 5% of the current harmonics or 10% of the current harmonics. So some countries, they don't even worry about current harmonics or something like that. To be example, China is a good example. So where they don't really foresee much on the harmonics point of view. So yeah, some countries, they'll be more stringent. Like if you say take Europe or North America, right? So they'll be more stringent on the grid polluting things. So they'll be expecting a lot of certifications. So again, this control adjustment comes into a major impact of the energy efficiency of that particular system. So having a complete overview about all the system, right? So coming to the topic which I worked on is like on the pumping system, which is the end user application that I worked on. So the component selection was like on a pumping system will be like pump selection, motor selection, coupling selection, all these things. And also it can be a variable frequency drive and proper grid maintenance. All these things will come in the proper component selection. And coming to the dimensioning, like I said, it is like kind of a designing the system without any like a oversized or undersized. So having this as a proper dimensioning will be like a pipes dimensioning and water system optimization. So how well we are optimizing the way of the water that needs to be pumped from the lower value, that is like from the suction to the reservoir, how well we are doing that. And third one is like the extended product approach. This is what I touched upon a little bit, like in case in the future, if you want to extend it, so how well you have designed that system. So the system should not be over designed for extending in the future, but the system has to be made in such a way that it should have a provision to extend its capability in the future. So that makes a lot of difference, right? So we should make sure that currently we are operating in the 100%, but we should be able to extend that in the future. So that's like our extended product approach. So that is very, very important to be considered in all the applications. And third one is the control adjustment. So in this, like I mentioned, so the VSD control, those things that I mentioned already, the scalar and vector, all these things, and the process optimization. So when it comes to the process optimization, in this scenario, in a pump scenario, I'll explain it, and then I can also try to correlate with the other applications as well. So one is like when you are talking about the process optimization. So normally, when it comes to an industry point of view, so we don't operate one pump with one drive, and that will be supplied from a single grid actually. So taking a supply from a single grid, so we try to control 3 pumps or 4 pumps in parallel. So instead of running a 10 megawatt pump, right? So what we try to do is like we make 2 5 megawatts pumps actually. So or like 2 megawatts pumps, whatever it is, whatever the combination that works for that system, we'll try to make that combination. The reason is very, very important. So when you're running only one pump for that particular application, right? So what happens is when you are of course, all the electrical equipments or all the equipments that needs maintenance, and that might go for wear and tear at some point. Actually, that might get a failure at some point. So machines are machines. So at some point, we'll get a failure. So during that failure, so when you're operating, when you're depending on only one system, one pump, right? So during that time, so your production will be completely zero, and you will not have any other inputs or outputs from the unit actually. So in order to avoid that, so we also have like instead of having one bigger unit, so we'll have a 3 or 4 multiple smaller units, so that whenever one pump goes to the maintenance, we can able to run the rest of the pumps, and then your production will still goes on actually. So that's the main focus. We always have the process optimization in almost all the industries. It's very, very important. And that's where the load shifting also comes into picture. So when you see that one of the pump is going for the maintenance or one of the pump is shut off, so the load will be shared between the other pumps. So and this load sharing will be it will be like kind of changed at a regular interval, so that the regular maintenance or the wear and tear on all the pumps will be the same. So that's the main focus on the energy efficiency. So I think now you will be able to get a good picture, like improving the energy efficiency in any system could be taken from this particular graph or this particular classification. You can able to design for your system as well. So coming to this, the system dimensioning topic I was talking, right? Why VFD? So there could be a lot of system dimensioning things, but why VFD is very, very important. So in a conventional system, so we have 100 units of energy that is being sent to a transformer, and this transformer is feeding an electric motor, and that will be feeding a pump, which is controlled by a throttle valve. And finally, we have a friction loss, or whichever that is happening in the pipe friction actually. So in electrical terminology, we have it like a the resistance, you call it, right? So the same resistance will be offered by the water on the pipes. So it's the same analogy, and so these are the losses that are incurred by each electric equipment. So let's say what is it? This is a losses that is occurred in the pipes. This is a loss that is occurred in the throttle valve and motor and pumps, so on. So when you see that, so we have a lot of energy that is being lost in the throttling valve actually. So when you want to control the pump from the grid, right? So during that time, you have lots of energy that is being lost in the throttle valve. So not only that as a major problem, but also during this throttle valve, so when you're controlling the throttle valve for the output of the pump, right? So during that time, your pump will be always running at the maximum speed, and your motor will be always running at the maximum speed actually. So you will not have the reduction in the speed, or when you want to have the reduce the control of the flow, right? So you just need to control the throttle valve. That's not the efficient way, and that will also consume a lot of energy. So that's why people have come up with a concept called variable frequency drive. or whenever the power electronic components got emerged, right? So people have come up with why don't we control the speed of the machine? So that's why they come up with the variable frequency drive. So with this variable frequency drive, so they can able to control the machine. So that machine could control the pump. And here we are completely replacing the throttle valve with the variable frequency drive. So with this variable frequency drive, we will be able to control the speed of the motor, and that will in turn control the speed of the pump. And then that will be controlling the flow rate or whatever the pressure, whichever the customer is really cared about. So likewise, now the biggest advantage is like we were actually eradicating this throttle valve, which is consuming a lot of energy, like 19% of the entire units. And that will be replaced with the variable frequency drive, which just consumes only 3% in terms of the throttle valve. So now, so if from taking from the output perspective, right? So output perspective to the grid point of view. So if the unit, if the utility just needs only 34 units of energy, right? So during that time, I was in the initial case, in the conventional case, I was supplying like 100 units of energy. But when it comes to the later point, right? So when we are working for 34 units of energy, that's the expected value. So for that, only 81 units is more than sufficient from the like the proposed solution actually. So you also have a 19% saved, that is from the throttle valve here. So that's the biggest advantage when it comes to when we are running the machine. But not only that, so during that time, so when you are reducing the speed of an motor or speed of a pump, right? So the pump has a tendency when the power of the when the speed of the pump is reduced by half, right? So the power consumed by the pump will be reduced by 1/3 actually. So we call this as an affinity loss of a pump. So we have a lot of laws, right? Like Newton laws or something like that. So the affinity laws are mainly for the pumps, which states like when you reduce the speed of the pump by half, your power will be reduced by cube actually. So that's really a biggest change. So that's why we have shown here actually. So like the power consumption for a throttling valve will be on the top graph, and the power consumption for the VFD will be on the bottom graph actually. So whichever the area between those two curves is nothing but the energy savings when you're operating the flow rate from 0 to the maximum value. So this maximum value will be of course dependent on the system. It can be sized from the 0.45 kilowatt to till up to megawatts as well. Yeah. So this is a system. Normally, it will be running any grid connected application or the variable frequency drive connected application. So this is how the end user application will be looking like. So you have a suction, you have the pump. So this is a pump, and this is a delivery. And normally, before starting any design of a system, so I'll be going through how we'll be designing a system actually, starting from the grid to the endpoint of the pump application. So I'll be showing you in a conventional way how we will be starting with the simulation, how we will be going through the real hardware testing. I'll showcase all the harmonic results. All these things are in the upcoming slides. So starting from the design point of view, right? So when an engineer first starts work on a project, so first he needs to understand like what is the system the customer needs actually. So if this is a system that the customer really worried about, so they have some suction, and that will be like, let's say, a few meters, like 100 or 200 meters, that is from the pump, and it is supposed to pump the water for around some 1,000 feet or something like that to the higher level. So this is the system dimension he needs. So the suction head is negative. The negative in the sense from the pump datum. So this is what we call it as a pump datum. The central radius of the pump, from there to the higher level of the water. That is what we call it as a static suction head. So if it is in the below the pump datum, so we call it as a static suction head negative. And this is the static delivery head, the same lines. It's from the datum of the pump to the higher level of the water in the delivery. So this is an impact that's shown with the static suction head negative. We also have a system with static suction head positive. So we don't know, right? So the customer may have a system like this as well. So we need all this information. So what is the customer is worried about? What is the suction head? What is the delivery head? All these things we need to understand for designing a proper grid or proper pump and proper motoring system, everything. So we need all this information. So having all this information, now we'll go into a system called MATLAB. So almost all of us would have worked on the MATLAB. So MATLAB is still, we are good actually. So we still run many of the simulation with MATLAB because of its like a more efficient or more good things. We have it in the MATLAB. So in the conventional method, like what we do is like we'll now understand what is the flow rate, what is the height that needs to be pumped, what is the pressure it needs to be pumped, what is the power maximum the customer can bear actually. So what is the power size it can go up to. So all this information will be obtained from the customer. So based on those information, we'll try to design a system from the simulation perspective first actually. So we have a centrifugal pumps. So, and we also have a piping system. We have a flow rate at whichever the interval we need. And we also need a differential pressure. A differential pressure is nothing but a pressure difference between the delivery and the suction. So we try to take those information, and from there we'll try to understand like how the water well is being sucked from the suction to the delivery point. So all this information will be put into a simulation, and then we'll try to run them. We'll make sure that all this information are running as expected. So that is the first and foremost thing. So on that perspective, so many of us would have already gone through the motor data sheet. Let's say if an induction machine or a permanent magnet machine, right? So we might have come across the data sheet which shows the graph between the speed and torque, and also it also shows the speed and power relation actually. So how a motor, when we are operating in which speed and what frequency, what is the amount of torque that it can exhibit, or what is the amount of power that it can draw. So those are the data sheet curves for a motor. And when I started working, that was my first time. I'm also seeing a data sheet of a pump. So the biggest surprise is like it's same exactly equivalent to your motor. And the analogy will be like in the motor, right? So we have a speed versus torque, but here we have a flow versus head actually. So many of us would have gone through an analogy between the electrical system and the magnetic system. It's the same like that. So we have an analogy between the electrical system and the hydraulic systems as well. So the flow will be equivalent to our speed, and the pressure will be equivalent to our torque. So that's how the analogy between the hydraulic system and the electrical system will work. And here I have shown the power with respect to the head as well, which is in our machines. So we have a power with respect to the torque, right? So we have the same equivalence here. And here also, so instead of the different speeds we are operating, right? So here we have a frequency at which the motor is being spun. So based on the motor, of course, the pump will be run. And based on that, you have the flow rate or the head, whichever you wanted. So these different lines are for each of the speeds, actually, speed values. Let's say for the starting from the 12.5 hertz to up to 50 hertz. So all these data are up to Indian market. So since my research was on the Indian market, so this was done up to 50 hertz. And you can start seeing it from the 12.5 hertz to up to 50 hertz, all these things. And like I mentioned, so in any of those systems, what we will be working right on the industry point of view, so we try to consider 2 or 3 systems in parallel. So in order to avoid the discrepancies when we are working for the maintenance, all these things. So during that time, so we need to make sure that things works fine when we are connecting them in parallel. So till now, I was showing only whatever that's happening inside this particular system. That's a pumping system. So now we have connected a motor, and that will be driven by electric drive, and that will be given by grid, which is actually through the circuit breakers, all these protections, everything. And coming to the output point, so we are actually having clubbing all the three outputs of the pumps, and we are giving to the reservoir, our delivery reservoir, and the input is taken from the input reservoir, that is a suction reservoir. All these things, three pumps takes from a suction reservoir and delivers to the delivery reservoir. This is how it happens. And finally, like what is the amount of harmonics that we are going to disturb on the grid side is our one of the major focus actually. I'll showcase what are the harmonics we have it, and based on the machines, like it's an induction machine, what is the harmonic that is available on the industry side, on the grid side, and if it is a permanent magnet machine, how that will be looking like. We also have a research topic that will be more interesting for you guys, like based on the harmonics, right? Based on the harmonics value, whether it's a third harmonic or fifth harmonic, which is a dominant, and also like patterns. We also have a regular patterns that is followed actually. So based on that, we can also estimate what is the type of motor that is connected, whether it's an induction machine is connected to the grid, or it's a permanent magnet that's connected to the grid. So that was one of the interesting topic for me when I stepped into this research, right? So during that time, our organization was working on estimating the machine that is connected to the grid actually. So without knowing any information about the grid, so we can estimate what is a machine that's connected. So yeah, so those are some of the important topics I can showcase in the next coming slides. So like as part of the MATLAB simulation, right, whatever we have done, we also need to hard code, or we need to write some programming for a few languages. Like for example, when it comes to MATLAB, here we have like the pressure or the efficiency or the power. So for all these things, we also need to take all these values. Like let's say, what is the coefficients for all these pumps, the MATLAB output values, all these things we need to be taking care. So yeah, so these are the general equations where I will be like inputting all these coefficients in all these values. Like you have the HA0 to the HA3, right? So for all these coefficients, I'll be trying to implement some of the values based on the power size of the pumps. So, and not only for the pressure, but also for the efficiency and power, I'll try to implement all these values into that one. So based on that, system will be changed, and your whichever the customer we are going to deliver, right, that will be also changed. Yeah. I'm not sure actually why this is happening, but I think I can erase that if someone would have done it unknowingly. Yeah. So if someone is having any questions, yeah, I can stop it and then I can go ahead for the question if that's what they're trying to do, or I can still proceed. Okay. So from the previous slide, so we have a different coefficients, right? So starting from the pressure, power, all these coefficients that I'm trying to show it here actually. So we have A0 coefficient, A1 coefficient, A2 and A3. These are for the power coefficients actually. So likewise, I mentioned for the efficiency coefficients and the pressure coefficients as well. So here, what I'm trying to do is like we are trying to generalize a machine based on the coefficients. Let's say from the grid values, whichever we obtained, right? So from the minimal power rating of the drive. So if you take this one, this is to be like a kind of a 10 kilowatts of the drive, from 10 kilowatts of a drive to up to around some 80 kilowatts of a drive. So I can able to correlate what will be the A3 coefficient actually. So when it comes to a 50 kilowatt of a drive, the A3 coefficient might be around some 0.65 or something like that, or 0.7, something like that. So what this will make easier job is like, let's say the customer is having a 50 kilowatt of a drive. I don't need to get the specification from the drive. So I already have all these grid values, all these values that are obtained from my research point of view. So from that value, I can able to take what is the A1 coefficient, what's the A0 coefficient, A2 and A3 coefficient. So based on that, I'll try to run this, I'll try to run my code. Okay, let's just go this. Okay. So based on this, I'll try to run my code. So with this, I'll be obtaining all the equations for all these equations for the power, efficiency, and the pressure. So with this, I can able to run my simulation. So like this. So based on that, we'll be obtaining what is the value at which the customer is expecting, and whether that is obeying really the grid regulations or not as well. So this is the real setup will look like that will be connected to the grid. So we have a grid connected here. Actually, behind this is a grid. And from this grid, we have the 3 electric drives which are connected in parallel. And so we have the measuring points here. So this measuring point shows the input of the drive and output of the drive as well. So from here, the output of the drive is connected to 3 pumps or 3 machines in parallel. So those 3 machines are connected to 3 different pumps. So these are the pumps and these are the motors actually. So from that pump, so this pump will take an input from the reservoir. So this is a prototype which we built actually. Instead of building for an entire system, first we start with a prototype. So with this prototype, so this will take an input from this tank, and it will try to run this 0.46 kilowatt drive. So the machine or the pump that I consider is a 0.46 kilowatt. So from here, I try to pump the water from the suction reservoir back to the delivery reservoir, back again to this tank. So during this time, we'll try to operate 3 different drives, and we'll make sure how this is affecting the grid harmonics, what are the major dominant harmonics that is available, all these things. And then based on the pump or based on the motor that is connected. So now I have connected all as an induction machine. I also have a permanent magnet machine. So I replace the permanent magnet machine with this induction machine, and then I'll try to study what is that is changing in the grid side, what is that is changing in the power. All these things will be studied, and then I have those results next that will be shown to you next. And these are the PQ boxes. And many of our institutions will have these PQ boxes still available. We have it. So these PQ boxes are for the measurement and storing the data. This can take a SD card as well. They have an SD card slot where you can store it for a week or something like that also, if in case you need it. So yeah, that is possible with this one. And yeah, so coming to the most important things like grid point of view. So here, like we have all the input and output values for your voltage and current. So here that shows the input and output values for both the reduced load for 25% and 100% as well. Not only on the 100%, but in all the industry or all the products, we try to operate them for 120% normally, 120% or also for 190% actually. So when the customer is unknowingly trying to operate it beyond the full rated speed, so let's say 120% or 190%, right? So the device has to go through for at least for a sufficient amount of time. Let's say, like for example, 30 seconds or 90 seconds or something like that actually. So based on the power it is being designed. So if it is operated for 190, it will go for like 9 seconds or 5 seconds, something like that, so that it will not really harm the customer, but it will turn off the system after a few seconds. So that's the main objective. And if you see here, you can see the harmonics at the input side of the drive. So for all the three phases actually. So this is a phase 1, phase 2, and phase 3. So yeah, so this is for both on the for the reduced speed, like 25%, and also on the rated speed, you can see the harmonics that is well developed actually. You have the fifth and third harmonic that is dominant. So I can show you that why the reason why, what is the, and many of you would have studied, right? So based on the pulse, what is the pulse of the inverter that we are driving it? Based on that, the dominant harmonics will be decided actually. Yeah. So these are the load profile for an induction machine. So when I consider for an induction machine, right? So when it comes to a grid point of view, what is the efficiency? What is the power drawn? What is the pressure, or what is the current drawn at the input perspective? For all the speed variables, like for example, from the rated speed up to the reduced speed of 70%. Of course, I still have up to like 50% or 20% for just for showcasing for you people. I just take it in the interval of 10. So with this interval of 10, so we have collected all these values. What is the torque exhibited by the motor and efficiency of the pump, motor, and variable frequency drive all together from the grid point of view, and the total efficiency in terms of percentage, and what is the power drawn in watts and HP. All these things I have shown it here. And this is not only for one particular torque load. This is for the torque load 1, torque load profile 2, 3. So likewise, we also classify based on the different torque load profiles. So that's also shown here. Yeah, so this is what I was talking about when it comes to an induction machine and a permanent magnet machine. From a grid perspective, if you see here, this is for a permanent magnet's input current spectrum, and this is for an induction machine input current spectrum. Like I mentioned, when it goes to the induction machine, right, you see most of the higher order harmonics from the 60th to 100th harmonic. From the 60th harmonic to the 100th harmonic, we have a lot of dominant harmonics that is available on the higher order. But when it comes to the PMSM machine, right, so we have the odd order harmonics that is more dominant and that is available on the lower side of the spectrum. So with this, if someone is coming up with some algorithm or something like that, yeah. So
சரி அப்ப பொண்ணு தனிமரமாலாம் ஆக்கல கம்முன்னு இருமே. என்ன வேணும்ன்றா இப்ப என்ன வேணும்ன்றா இப்ப நம்ம காது குத்துறது ஒரு இதாயிடுச்சு. அந்த
okay. So when coming to this, like I mentioned, so it can be either a PMSM machine or induction machine. So based on the harmonics that we are showing it, right? So whether it can be a higher order harmonics from the 60th to 100th order harmonic, So that will be more dominant on the induction machine side. When it comes to the permanent magnet machine, we have a lower order harmonics or the odd order harmonics, which will be higher dominant. Yeah. So these are some of the test results on the grid point of view when it comes to a proper grid, right? So how the grid should be on an induction machine or a permanent magnet machine at rated speed. I've shown it here. So here you will be able to find for all the phases like phase 1, phase 2, phase 3, or you call it as RYB on the output side. This is on the input side or for the induction machine. So compared to them, how the active power, reactive power, all these things are shown here actually with the phase delay, what is happening. And you also have the TSDs on the voltage, current, power, everything. Both as well as for the induction machine as well as the permanent magnet is shown here. Yeah, again, coming to a comparison between induction machine and permanent magnet machine from the grid perspective, with 25%. The 25% is kept as a common factor for both the machines. We try to compare what is happening for a induction machine. If you see that, so like I mentioned, on the lower order harmonics, it will having a more dominant. And with the permanent magnet machine, it will be on the higher order harmonics from the 60th to 100th order harmonic on the grid perspective. That makes a lot of difference between the induction machine and permanent one. And coming to the rated value, the induction machine is having the rated speed of 50 hertz, and the permanent magnet machine will be having a rated value of 150 hertz. So here, when you see that there are a lot of nil harmonics that are present when it comes to the higher order harmonics. When it comes to the induction machine, right, like I mentioned, so you have a lot of higher order harmonics available here. And the more dominant on the PMSM will be on the lower order harmonics here. So a lot of comparisons between the induction machine and the permanent magnet machine, starting from the reduced frequency to the higher frequencies. So this a comparison or a control algorithm that will help us from the grid point of view. So how we are going to classify the induction machine with the permanent magnet machine. So that would be a good research if someone is willing to take it up. So which currently some industry people, they are working on it. Yeah. And yeah, like I mentioned, the power quality parameters from the grid point of view will be like you have the kilowatt and reactive power and all these, the power factors, VTSDs, ATSDs for starting from the torque values. So for this, I have the maximum value of 0.5 torque and from the minimum value of 0.1. So what is the minimum value, maximum value, average value? So all these values are obtained from the PQ box or thing. And from there, I'll try to list on them, like which is the dominant value, like it can be fifth order harmonic, third order harmonic. Yeah, likewise, you can able to define them and what is the power consumed at each level. So that could also be defined here. So till now, I was explaining about the conventional method of testing a grid with an electric machine or with the application. I have taken up a pump application. So now I'll be moving towards a trend, what is currently industry is following. So currently we don't do the previous kind of testing. I mean, in not all the cases. So the conventional testing will be like initially the requirements will be obtained. So a few months will be working. For example, 2 to 3 months, people will be working on the developing the simulation. So once the simulation is ready, so then they will be moving towards developing the hardware. And once the hardware is testing is done for a few months, let's say 3 or 4 months. So after that, they go for a testing actually in the hardware. So they go for a regression testing on the software perspective. On the hardware, they go for a high pot testing. Like they try to run it on the really very high situations, like more than 100% of the rated speed. They try to run it in the very high temperatures, and they try to make it as an input shorting test. All these things will be done. So during that time, so not all tests will be successful at the first try of testing itself, right? So as a researchers, we might also be knowing. So when we are doing our research, the first time might not give us a desired result. So we might end up with some kind of blasting of a capacitance or some kind of saturation of an inductance. Something might be happening, some disadvantages or some kind of mishappening might be happening. So what that will happen is like because of that problem or something like that, so you might have to sometime redesign the entire hardware from the beginning. So the 2 months of work which you have put might be wasted, or you might have to, in case if the customer is coming back to you and he is telling like he needs a small change in the design. So you need to go back to your simulation as well actually. From there, the simulation needs to be changed. Then the real hardware needs to be modified. Then you need to perform all the regression testing on the software side. Then you need to perform all the real testing, the real hardware testing on the hardware side as well. So all these things will take really a lot of time. It will consume more than like based on the project, right? So it can consume from months to kind of a year as well. So this should not happen. So for this, people have come up with the recent concept called hardware in loop or simulation in loop, software in loop, those kind of steps. So from there, what happens is like when you are getting the requirements from the customer, so you also start designing all these things from the simulation, from the hardware, from the software perspective, everything. So with that one, you'll be able to obtain what is the needed things. Let's say if this is the required output of the customer, right? So for that, what is the software that needs to be done? What is the hardware that needs to be done from the day one itself? And every day the regression will go on. The regression in the sense, for all the hardware, you need a software to be modified, right? So for that software, what is the regression that needs to be done? Like every day, every night, the software needs to be run on the nightly basis. So based on that, so you will have an output or the result that will be shown here. So based on that, that results will be shared to the both grid team, hardware team, everyone, the motor, whichever the team they are working on. So if there is a problem with the powertronic device that is spoiling a grid, right? So automatically the person who works on the powertronic component will be modifying that particular parameter which he has modified yesterday. So the next day he will modify it, make sure that things where everything is good. So this is like a kind of a continuous improvement. We call it as a CI integration. So every day we try to improve the system one by one. So at some point, like let's say completing a day 100 or something like that, or end of the year or something like that. So we'll be having the complete product with the software, with the hardware, everything ready. So that's how things will work on. Yeah. Okay. So, okay. I assume like it was like done unknowingly, but in case if someone needs some explanation on that, yeah, feel free to speak out. Okay, so after we make the hardware and loop system ready, right? So it was similar to our MATLAB. So, but here we have the real hardware. So after things are done, we go to the SCADA panel. So this is like your LabVIEW. If people have worked on the LabVIEW, right, we have two different windows. One, we have it like for drag and drop things. We make the simulation, everything. Another one to view the results, actually. It's the same, it's the same scenario. So here, one is for the simulation, another one is now for the viewing the simulation results. And yeah, so all these things are observed in this particular panel, that is a SCADA panel. So here you have what is the speed at which motor is running. So based on that, you have the current that is shown here. And from these, we try to observe what is the current at which, for example, 900 RPM is drawn. All these things could be observed. Yeah. So again, in case if I'm increasing or reducing the speed, how am I going to observe? Like, for example, you have ABC components right on the grid. All these things could be observed. It's not only observes your phase and neutral components, but also you have an alpha and beta components, right? When it comes to a two-phase to three-phase, all these conversions, you'll be able to witness all these scenarios actually. As a control engineer, you can able to see everything. And having everything, all these data will be stored in the cloud. So we don't trust any local machine or something like that. So let's say if you are working on some power laws or grid components, right? So we'll try to store all these codings, whatever we have done in the grid. So we call it like kind of an Azure. So this is Azure is a product that is developed by Microsoft. And almost all the industries they are working on Azure. So whatever the code they are working on, they'll try to push it to the cloud. So it can be accessed by different engineers in different locations. So if you can see that if some of the engineers they're working on India, some of the engineers they're working on the Denmark, right? They can share their coding between those two people, and all these people can work on the same product. So yeah, that's the biggest advantage of working with the cloud. Anyone can access the values, and anyone can start working on that. Yeah, for understanding, this is how the code will look like. So this is one of the mains program for controlling the grid main voltages. We have a flying start program, and we have a rotor reduction. So all these things are some of the testing that we are going to do it. And from there, we will be showing that what is the drive that is considered, what is the motor that is considered, what is the grid that is we are using it, whether it's a XR ratio, SC ratio, all these parameters for the grid, everything will be considering it actually. how good we are going to control the grid, how we are going to make the grid more stable. All these things is what makes the entire system more and more intelligent. Yeah. Finally, running this test case will give you the results. Either it can be a pass or fail. So if it's a fail, what is a fail? So now I got the result as pass. So I was able to run the machine with no problems. Everything is good. So sometimes if you are running the machine, you might end up with some kind of a problem or something like that. So you might face like this problem is like due to the machine is not properly connected, or one of the phase might be missing, or the grid has some the harmonics of the grid will be much higher than the permissible level. So all these are the different values the test might fail actually. So we need to make sure that the test is more intelligent, and that is really controlling on the grid point of view as well, making the grid as well stable actually. And we are abiding by all the regulations like IEC or UL, all these regulations. Yeah. So coming to the end of the presentation will be like I mentioned. So we have some of the research opportunities. Like as part of, I was working on my research area, and when I started working for a company, so during that time I faced a few gaps which are still available. Sorry. So till now I was talking about like when I started the research, it was like we have like IE2 machines, IE3 machines, kind of lower class of efficiency machines that are available in the market. But now I guess we were working towards IE4 and IE5 machines, which is like a supreme efficiency motors that are available in the market. So someone can think about it like how the efficiency is different from the lower one and the higher value. What are the advantages when we are using the higher machines, and what are the different disadvantages when you are moving from the lower efficiency machines to the higher efficiency machines? Of course, there is a trade, like you need to compromise on the cost when you are moving towards the higher efficiency machines, and how well you are going to get the return on investment when you are trying to put a higher efficiency machines like IE4 or IE5 machines on existing IE2 machines. So likewise, that could be one of the good topic. And second one could be like estimating the losses. Like one topic I was explaining when I was going through the slides is like estimating what is the machine that is connected from the grid point of view. You can estimate what is the losses from a grid. So having a grid in your control, you can able to estimate what is the loss that is incurred in each element. Like for example, power cables, your VFDs, sharp couplings, everything. So that could be a good topic. So these are some of the key things which I got immediately in my mind when I was trying to prepare the presentation. But yeah, but still I can we can think about a lot of topics actually in this particular area. I don't want to overfill all these things with the complete slide, but still we have a lot of things that are available in the industry that is unaddressed. You, some of the researchers, they can start work on those particular topics or areas, or you guys can able to contact me in person, so I can share some of the inputs in case if you're already working on some topic and you want to know how that could be connected to a intelligent system like a machine learning or data science things. So I can suggest you guys like, yeah, this you can do it. So this is what industry is looking for. All these things I can able to, yeah, I can able to give my suggestions if you need. Yeah, I think that's all I have it for today. And yeah, and I can answer some of your questions if you have it, or you can write those questions to me if you don't feel like asking it. I'm fine with anything. So yeah, that's all I have it for today. If you guys have any questions, I can take it up in the next 5 to 10 minutes. Or like, yeah. Hello.
Dear participants, you can please unmute your mic, and if you have queries, please rise up. Arun sir,
Yep. Yes, sir.
there is a question in the chat box, sir.
Yeah, exactly. I was going through that. Yeah. So, what is the scalability of IoT in large-scale smart grid implementations? So, when it comes to a scalability, like as of now, Danfoss is not working more on the scalability part or the smart grid implementation. So, we mostly work on like kind of how we are going to eradicate most of the harmonics in the grid and how to monitor the grid, all these things actually. So, but I can still come up with your response. Yeah, and you can write to this mail ID. I can share my mail ID. Yep. So if you're fine, you can share me your mail ID. I can reply back to your mail ID, or yeah, you can contact me through this one. I can get in touch with my colleagues or someone who has already worked on this. The scalability part, I can get back to you.
Dear participants, any other questions?
And Lijo sir, hope you're not asking me the contact number. If you're asking me, I'm fine. I can share. I think I already have your contact number. And yeah. Oh, I'm sorry. Yeah.
Dr. Arun Shankar, sir.
Yes, sir.
Yes, sir. Thank you so much on your wonderful presentation on the topic of advanced IoT solution for smart grid monitoring and control. I hope this session has enlightened the faculty fraternity in all the aspects of future research as well as the teaching. And we have also learned what are all the tools and implementations which have been done in the Danfoss Industries, Lowe's-Park, USA. And hope this session has have gained a fruitful knowledge in all the aspects of faculties as well as research scholars as well as industry persons. Thank you, sir. And dear participants, dear participants, please stay. There is a feedback has been posted across the chat box. Please fill the chat box, and we'll be sharing the presentation of today's session in a Google Drive. And at the end of this 6 days program, we will be sharing the Google Drive towards you. And I repeat, dear participants, please fill the feedback form which is available in the chat box. And if any participants who have not yet joined in the WhatsApp group, the WhatsApp group link is also available in the chat box. Please join it as we'll be stay connected in the WhatsApp group in your future communications. Thank you all.
Narayani.
Good evening, everyone. It gives me immense pleasure to welcome you all to this event today. We are honored to have with us a distinguished academician, researcher, and leader in the field of electricals and computer engineering, Dr. Vijay Kumar Krishnaswamy. Dr. Vijay Kumar Krishnaswamy, an associate professor at the Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram, Chennai, earned his bachelor's degree in electrical and electronics engineering from the prestigious Coimbatore Institute of Technology in 2006. He went on to achieve an All India rank of 358 in the GATE exam, enabling him to pursue his MTech in Power Systems from NIT Tiruchirappalli. His PhD research journey at NIT was so equally impressive, where he was also selected for the prestigious Canadian Commonwealth Fellowship at the University of Saskatchewan, Canada. In recognition of his groundbreaking PhD dissertation, he was awarded the POSOCO 2014 Doctoral Award, placing his work among the top 10 across IITs and NITs. Dr. Vijay Kumar has further enriched his expertise as a postdoctoral research fellow at Nanyang Technological University, Singapore, and as a visiting professor at the University of Saskatchewan. He numerously accolades include the Young Scientist Award by SERB DST in 2015 and recognition as a young faculty fellow by the Ministry of Communications and Information Technology. Apart from academia, Dr. Vijay Kumar has served as an assistant professor at MNIT Jaipur and as an adjunct faculty at the National Center for Disaster Mitigation and Management. His research endeavors continue to inspire innovation in fields critical to society. Let us all join hands in extending a warm welcome to Dr. Vijay Kumar Krishnasamy and look forward to his enlightening session. Over to you, sir.
Good evening, all. I hope I am audible to all.
Yes, sir.
Yeah, sure. Thank you. Good evening, all. It's my great pleasure to be part of this program. And thanks for that invitation to deliver this talk on this FTP. Just today, I'm here to talk about role of smart grid in sustainable energy management. Just I can continue. If you have any question or discussion, please just you can unmute and you can interfere me so that I can answer questions. I hope that audience can unmute and ask the questions, right?
Yes, sir. Permission.
Yeah, sure. Thank you. Okay. My screen is visible? Please confirm it. So my slides are moving?
Yes, sir.
Yes, sir.
Yeah, sure. Thank you. So if any problem, please let me know. So, right. So when we come into that energy management, so just we have to understand that energy pyramid, that's very much important. So here, when we come into that energy pyramid, just we can look at that energy pyramid. So just we are in the bottom of that energy pyramid, we are having the assessment. So first we have to assess that various equipments, devices in the system. Then just we have to go with that conservative measures. So that is we can call it as a tier 1 action. So in that tier 1 action, basically depending upon the user behavior, that is a consumption behavior of the users. So by changing the user behavior, we can able to save the energy. So here we do not invest much on this energy conservative measures. But when we go into that next stage, that's a tier 2. So in a tier 2, we are having the energy efficiency. So in that energy efficiency, just we have to replace some of the devices in the system, or we can say is whether it's in any industry or if we talk about any kind of system. So just we have to invest on replacing some of that energy efficient devices so that we can able to save the energy in that case. So when the pyramid goes up, the complexity and cost also will increase. So that's what, as compared to that energy conservative measures in energy efficiency, we have to invest much on to save the energy. But here, at the same time, on top of it, we are having that alternative energy sources. So by integrating that wind photovoltaic systems into the system, then we can able to achieve that energy conservation management. So in that case, in the alternative energy, that is a renewable energy sources, the cost is higher. At the same time, the complexity also come into the place. So that's what we can say in the pyramid from bottom to top. If you move, that complexity and cost will increase. So here, yes, in this case, so if you have any question, you can unmute and you can ask. Otherwise, you can please mute. Yeah. So here, when we come into that energy transformation by 2050, So the main objective of this energy transformation is to reduce that carbon emission by 70% than the current level. So here, that's what most of the countries, they are promoting this renewable energy sources to reduce the carbon emissions. At the same time, because of that penetration level, that energy cost also is coming down. We can say in the 10 to 20 years back, if you want to generate 1 kilowatt, that means 1 unit of energy from that wind or photovoltaic system, it costs you around 15 to 16 rupees. But now when we come into that solar or wind energy conversion system, the energy cost is almost, we can say, is 2 rupees per unit. So that's what the energy cost also is coming down. At the same time, the reason for it, the technology. So when we come to that solar photovoltaic system, the panel cost is around 70,000 rupees or 75,000 rupees in 2005 or 2000, the 200-watt panel. But now the panel cost is significantly reduced. Even 250 or 200-watt panel, you can buy for 7,000 to 10,000 rupees, right? So that's what we can say. The energy cost also is coming down. Then when we come to that other objective is greater economic gain. So it's a win-win for the utilities as well as the consumers. At the same time, the payback period also is coming down because of this integration of these renewables. And on top of all, we can say that to enhance the energy security of any country, we can say the reason is very simple. So in any country, if we take, almost even in India, 80% of the power we are generating from the fossil fuels. So just we can say oil, and we are depending upon the oil and coal. Once if we are having the scarcity of this fossil fuels, so when the scarcity comes, means it's even we can evident that from the Russia-Ukraine war. So even most of that oil and coal we are importing from some developed countries or some EAE countries. Because of any geopolitical issues, so we will be in the greater demand of this resources. So that time, we could not able to meet out that low demand. Even the Europe is facing recession because of this natural gas supply from the Russia. So because of that war, they have stopped entirely that natural gas to the Europe countries. So that's what they are in that greater demand. And when we come into the energy access, by integrating these renewables, we can able to achieve 100% energy access, right? So even 4 to 5% of that locations are far away from that distribution networks. So in those areas, if you want to provide that electricity, so we can able to design the system by using wind and photovoltaic systems. So on top of all, we can say in socio-economic perspective, we can able to create a lot of job opportunities in this renewable energy sector. So this is some of the estimation is given by IRENA. So in this, just we can see by 2050, the electricity generation is going to touch by 55,000 terawatt hours per year. So out of this energy, 55,000 terawatt hour, so almost we can say 86% of the demand, or we can say that the electricity generation going out from this renewable energy sources. So only just they're estimating that 20%, almost 14 to 20% of the energy they are going to get from the fossil fuels. So in this 86% of this renewable energy, if you look at that composition, so almost we can say 6,000 odd gigawatt of the power going to come from that wind energy conversion system, and another 8,500 odd gigawatt of the power going to come up from that solar photovoltaic systems. So here we can say that 1/3 of the power going to come from wind energy conversion system, and another 1/3 of the power going to come from solar photovoltaic system. So these two technologies will dominate for generating the power in renewable energy sector. So that's what the government's also focusing much emphasis on these two technologies, wind and photovoltaic systems. So when we come into the photovoltaic system, if you look at that growth rate, so the growth rate is higher. We can say is 15 to 20% CAGR. So that we are getting from that solar photovoltaic system. And wind, if you look at that, 10 to 12%, and bioenergy and others are, in a single digit growth rate. So that's what the reason is very simple why that PV installation is increasing in worldwide. Because when we talk about the photovoltaic system, it's a static device. So we do not have any kind of rotational parts. So the maintenance is not there. At the same time, we can able to have that power supply from milliwatt to megawatt level, right? So that's a reason they are concentrating much on that solar photovoltaic system than that wind energy conversion system. So we can say that growth rate, if you look at that, almost 20 to 30% CAGR in the year of 2018 to 2020. So that's a huge growth rate. Even if you're having a 10 to 12% itself, it's a good. But here, if you look at that, we are having almost more than 20% growth rate. So that's what just we can see that a lot of technology changes it's happening in this photovoltaic systems. At the same time, if you look at that wind energy system, so it's a very old technology, we can say, as compared to photovoltaic system. The wind energy conversion system is very mature. The reason is from 1980 itself, we are having the wind turbines from that capacity of 50 kilowatt to even at present, we are having a 10 megawatt single turbine. Even a single unit turbine, we are having the 10 megawatt. Even if you look at that diameter of this wind turbine, it's almost we reached 164 meters. So even the diameter, the rotor diameter itself, it's a 164 means the tower height is almost more than, we can say it's a 180 meters. So even the single tower, the wind turbines having the 180 meter height. And here the technology also, it's keep on changing. Earlier, just they have used that fixed speed wind turbines. So once you are using the fixed speed wind turbines, we need not to have any power converters between that turbine and grid. So here we can say there is no power electronic converters in the wind turbines. But in 1995 to 2000, they have used that partially variable speed wind turbines. So in this, they have used the rotor resistance control method in the slip ring induction machines. So here the converter rating is very, we can say is a 10% of that machine rating. So that's what they are saying is a partially variable speed. And from 2000 to 2005, we can say we can, even at present, whatever the wind turbines we are getting, those are variable speed wind turbines. So we can able to control the speed up to 100%. That means by controlling the generator, we can able to control the speed of the turbine. So when we talk about the wind turbines, we can discuss much on this, why we need power electronic converters and all we'll discuss later. But at this stage, just I want to convey here is, so here, when the time goes, the technology also it's enhancing. Then here, the power electronics plays a huge role. So the reason for power electronics here is to implement the maximum power point tracking algorithms. At the same time, if you are using this wind turbines for standalone wind energy conversion system, just you have to go with that energy management and everything. Even if your wind turbine is connected to the grid, then you have to follow the grid codes, right? So for that, power electronics plays a huge role. Then we'll discuss in that wind energy conversion system slides. So here, when we talk about that individual size of the turbines, it's almost we are reaching 15 megawatt. So this 15 megawatt wind turbines are located in that offshore. And here the power electronic converters also we are using it to implement the maximum power point tracking. So when we come into that India, so here in India, just if you look at that from 16 to 24, 2016 to 2024, so almost we are having the CAGR rate of 15%. That means Every year we are increasing the 15% of the capacity. So almost we have reached 145, almost we can say it's 140 gigawatt of the power we are generating from this renewable energy sources. So here, as per target of the MNRE, they are planning to achieve 175 gigawatt, but by 2030, they are very positive that they can reach that 175 gigawatt of the power from the renewable energy sources. So here, if you look into that renewable energy capacity breakup, so almost in 2024, 82%, we can say, sorry, not percent, 82 gigawatt of the power we are getting from the solar photovoltaic system, and 46 gigawatt of the power we are getting from the wind energy conversion system, and others just we can say is a small hydro and biogas power plants, almost 10 to 15%. So almost we can say that wind and photovoltaic systems will dominate the renewable energy sector. So when we come into the smart grid, so here it's very important to note down when we look into the power system, just in a power system, normally just we'll talk about generation, transmission, and distribution. So normally we'll say it's a GTD. So in this GTD, when we say in the power flow in the system, so in the power flow in the system is unidirectional. So we do not have any bidirectional power flow capability in the conventional GTD. So when we come into today's grid or today's network, if we talk about, just we are integrating all this wind and photovoltaic system into that distribution networks. So if you are integrating this wind and photovoltaic system into that distribution networks, we can say that the sources are distributed in that network. At the same time, that sources are very near to the loads. So whatever the power is generated, that directly pass it to the loads, and whatever that excess power that can be sent it to some other locations. So here that we can say the sources are connected near to that load, so there is no transmission and distribution losses. So that's what most of the time not most of the time. So when we talk about wind and photovoltaic system in the power system side, we'll say is the distributed generation sources. That's what we are calling them as a distributed generation sources. The reason is we are connecting this wind and photovoltaic system in the distribution networks. So here, when we come into that smart grid, so smart grid is not a new grid. It's an existing grid. So in the existing grid, what we are doing is just we are enhancing the features. So enhancing the features means we can say the person is very smart. So the person is smart means he could be able to communicate with the people or communicate with the society. The same way, if you want to communicate in that system and even if we take a power system, then we have to deploy a lot of sensors. At the same time, just we have to establish the communication among all the devices. That's very much important. So once that devices are communicating to the neighbor devices as well as in the system, we can able to include the intelligence into the system. So that's what just we are having that we are leveraging this artificial intelligence technologies and machine learning and everything we are leveraging for enhancing that operation of that grid. So here, if we talk about that conventional power plants, you are having thermal power plant and hydro. And here, when we come into that, I mean, in the generation side, changes are happening, but most of the changes or developments happening in the consumer side. That means in the distribution side. Even earlier, people talk about the distribution networks. In the distribution networks, the power flow is unidirectional. But now, in the distribution network, the power flow is bidirectional because we are having a lot of sources and devices in that distribution network. First, we'll go one by one. So when we talk about the factories, so earlier, even we are talking about industry 4.0 and industry 5.0. So in Industry 4.0, we are going with the full automation of the system. So in the 5.0, it's going to talk about a lot of technologies side, but in the 4.0, it's automation side as well as energy efficient side. So that's what, if you are going with that energy efficient side, then you have to put a lot of smart devices in the factories to automate the system. So that's what we can say. We are having the frequent on and off of the machineries in the system, right? So that also we can say it's a variable one. So we can have the stochastic nature. And when we come to the residential buildings, so in the residential buildings also, it's a lot of developments happening. Even we are having the rooftop photovoltaic systems. We are having a lot of smart devices in our home. So that, I mean, people might ask that why we need to go for smart devices. So smart devices is not for luxury or, excuse me, it's not for luxury, or we can say that not for show off. So only for energy conservative side. So even if you are saying that air conditioners or refrigerators in a home, earlier just we used to buy the air conditioners or refrigerators by looking at their ratings. So whether we can go for 3-star rating or 5-star rating, right? So then now there are a lot of things is happening. Even the refrigerator and air conditioner, we are having that inverter-based air conditioners or inverter-based refrigerators. So on top of all, now people are advertising that smart refrigerators or smart air conditioners. So what is smart refrigerators or air conditioners? Anybody having any idea about it? What is a smart refrigerators or smart air conditioners? Yes. So the thing is that this refrigerators and air conditioners, we can able to connect to the network. So network means it's a communication network. So that even your air conditioners and refrigerators can communicate with your Wi-Fi router. So wherever you are, you can able to access your refrigerators and air conditioners. So people might ask that for accessing my refrigerator and air conditioner remotely, so I need to spend extra 5,000 rupees. I mean, even if you are going with smart refrigerators or air conditioners, the price is higher side. So people might ask that why I need to invest much on this smart refrigerators and air conditioners. Any idea? So why we are going for this? Even the price is higher than that inverter-based air conditioners or refrigerators or 3-star, 5-star. The prices are higher, but still people are buying it. So why? How we can get benefit out of it? Okay. So here the reason is very simple. So now if you are saying at present tariff, so the present tariff is based on the we can say based on the number of units which we are consuming. So it's not based on the time of use, we can say. So I can say if I'm saying 500 units you consume, then more than 500 units, the prices differ. So that I have to pay different prices more than that units. But here, when we talk about the time of use tariff, so even we can take Ola and Uber based on the demand, they are having the dynamic pricing, right? So the same, you can assume that we are having the variable tariff or time of use tariff. Then that time, these smart refrigerators and air conditioners come into the place. You can able to schedule your loads. So whenever the price is lower, that time just you can schedule your loads. So your washing machine or refrigerator, air conditioner can run. So when the price is higher, that time just you can, I mean, your system can turn off all these devices based on that requirement. So in that case, we can able to save the electricity bill. So not only that's good for the consumers as well as that utilities. The reason is a win-win for utilities as well as the consumers. So you can get benefit out of it. You can reduce the electricity bill. At the same time, that utilities, they don't want to go with the new power plants to meet out the demand. So whatever the power demand is increasing with the existing resources, they can able to meet out. So that's what people are looking for it. This smart refrigerators and air conditioners. So that will give the benefit to the users as well as utilities. So the same in that commercial buildings, we can say the office spaces or any commercial building we can talk about. So here also we can go with a lot of energy efficient devices and smart devices. So all the buildings are connected to the network so that we can able to go with that, demand response management. So that will be helpful for the utilities. So that's what now people are moving towards the intelligent into this loads. At the same time, if you look into that other side is electric vehicles. So even there is a huge development that's happening in the electric vehicles. So in this, if you could see here, when we are talking about electric vehicles at present, we are considering these electric vehicles are only as a load. Even you can purchase Nexon or you can buy any EV. So those are the unidirectional charges. You do not have any bidirectional charges or smart charges. So these EVs will be considered as a loads into your system. So that means that just you can say that to the network distribution network, this will be considered as a load. So you do not able to discharge these batteries, right? So if you are having the bidirectional charges, then you can able to discharge it. Otherwise, it will not be possible, right? So that's what even this. Another thing, if you talk about the electric vehicle, so how much of time we are using the vehicle? Suppose if I'm having that car or vehicle, so how much percentage of the time I'm driving my car? If you consider for a longer duration, 6 months or 1 year period of time, if you take, so how much percentage of the time I can I'm driving my vehicle? Any idea about it? Any guess from the audience side? I hope you are getting my question. How much percentage of the time we are driving our car, or if you are having that car, how much percentage of the time you are driving your car for the 1 year period of time? Any guess? Any numbers? Sorry. Yes. So 10%, 20%? Sorry. Prakash? Yeah, just we can say that we are we are driving almost less than 10% of the time, we can say. It's only 6 to 8% of the time just we are driving the car. Then most of the time, 90% of the time, just we are parking our vehicle on the parking lot in a home or in our office. So in that case, instead of ideally parking the car, so whatever the batteries you are having in that vehicle, you can use it for demand response management. So demand response management means the same. If you consider that variable tariff system, so that time whenever the price is lower, so just you are parking your parking lot, so that time you can charge your vehicle. So whenever the price is higher, then you can discharge and you can sell your energy to that network with a higher cost, right? So because that time price is higher, so that we can make profit out of it. So that's what, no, instead of, and for that, no, you have to aggregate all the electric vehicles in the region. So at the same time, once you can able to aggregate it, you will get a very good energy storage capacity. So instead of using the physical storage in that renewable energy side, in that distribution network, once you can able to aggregate this, all the EVs, that energy storage, you can use it for assisting the physical energy storage in the system. That means physical energy storage means it's a battery energy storage, right? So because by aggregating itself, we can able to get some energy storage capacity. So that can be used here to assist for the physical energy storage system, right? So this what it's there are a lot of developments is happening in the distribution network side. At the same time, here, if you talk about wind and photovoltaic system, so here the wind and photovoltaic systems are we can say is the intermittent nature. So we could not able to get that constant power from these resources. At the same time, there is a lot of changes happening that loads also. The loads also is a variable one. So just here, the energy management is very much required to meet out that supply and demand. Otherwise, just your system going to the unstable, right? So that's what the energy management in the smart grid plays the huge role. So here, the smart grid, if we talk about in a smart grid, we can able to establish that communication among the devices, so that if you could able to establish the communication, then it's easy for you to implement the demand response management as well as demand side management, so that you can able to achieve the efficient energy management in the grid, right? So that's what now we are leveraging that various technologies like IoT, AI, and ML in the power system. So when we come to that smart grid or smart city, so we are using variable IoT solutions in that different levels. So when we go into that operator side, so just to control that center, and they consider as an enterprise, so that for them it will be very easy to manage the hazards. And here in the generator side, we can say that we can able to operate that generators efficiently if you could able to communicate with the different devices in the system, and we can say that we can meet out that supply and demand. So once if you are having the communication at all the sites, then it will be very easy for you to make the decisions. So that to meet out that supply demand match also it's possible with the implementation of that IoT. And here for operators side, if you consider that smart grid, they can able to make that renewable sources as a dispatchable power source. So how we can say that renewables are dispatchable power source? If we talk about fuel cell, or if you talk about conventional power plants, so these conventional power plants are dispatchable power sources. But when we talk about the renewables are not dispatchable. But by having that efficient energy storage technology as well as IoT into the system, integrating that IoT into the system, we can able to make this renewable energy sources as a dispatchable power sources. So that's very much important for energy management in the system. So here in that different sectors, we are having that different types of smartness. So even talk about the buildings, homes, smart buildings, and we are having a smart water. Those also is the energy systems, smart water, smart mobility, as well as now people are talking about data centers. So when we talk about the data centers, that data centers can, sorry, excuse me. So these data centers can consume a lot of electrical energy, so that the demand also again is going to be higher. So that's what just we are, once you are saying that our country is developing, then your generation also should be enhanced to meet out the demands. So buildings and homes, we are having the different IoT solutions in that area. So we are having the different IoT devices. That's we are having a sensors, and we are having a very cheap processors and microcontrollers. So by having the microcontrollers and sensors, we can able to collect the data, as well as we can able to, by using the microcontrollers or embedded controllers, we can able to communicate to that a node device. We can call it as a node devices. So those node devices will be connected to the cloud, and we can send the data to the cloud, and we can do a lot of computations on the clouds, in the cloud side, cloud computing. So in that cloud computing, we are having a GUI, so we can able to access, as well as we can able to monitor that energy consumption pattern of any home or any industry. That it's possible. So here people are working on the different devices, sensors, as well as they're working on the different communication protocols for integrating these devices into the system. So here, when we come into that EV, so EV we talk about V2G and G2V. So V2G, G2V is nothing. It's very simple concept. We need not to think much on these names. So here, vehicle to grid means it's very simple. You can discharge your EV to the network, right? That means you are discharging the battery in the EV and you are sending the power to the grid. So that's a V2G. And G2V, we are charging the batteries in the electric vehicle. So that's what we can say. In that G2V, we are having the blue line, just we are charging the vehicle. And here in that V2G, we are discharging the vehicle. So only thing is that we can have the bidirectional converters in that charger points. So that will take care of this bidirectional power flow. However, just we should have that control unit. So the communication also should be there. For example, so when you need to discharge the batteries, when you have to charge, so we have to look at the tariff of that electricity price. Based on that, you have to charge and discharge that vehicle. At the same time, if you are planning for a trip for another 1 hour, so just you have to maintain that 80% of the SOC in your vehicle, then just you have to you have to be you have to give information to that control unit. So that should not allow your vehicle to discharge that energy, because because of the electricity price, if your vehicle take the decision to discharge it, so when you are planning to go out, so that time your battery will be discharged, so you can't able to make the trip. So for that, you have to develop that very much useful algorithms as a consumer centric, so that will be useful for this V2G and G2V. So for that, there are a lot of things need to be done. So here we are saying that we are having the bidirectional converters. So in this bidirectional converters also, we are having the different types of converters. So there is a huge area to work on it. At the same time, establishing the communication between your grid and vehicle also, it's a huge task. So that's what they are working on, the various communication protocols for the EV. So now earlier just we have talked about only that V2G and G2V, but now people are talking about V2X. So V2X means V2 anything, vehicle to anything. So vehicle to anything means we can say that vehicle to grid already we have discussed. And if you are having that load, suppose if you are going for a long trip and you want to power up your tent or power up your devices, then just we can say V2L, we can say, just you can discharge your battery and we can able to power up this loads. And vehicle to vehicle, so even you can, if your friend is running out of the charge, then you can give a loan to him, right? So that also is possible. That's what V2, we can say it's a V2V. And when we come to the homes, even now in a home for reliable power supply, we are having the UPS system. So in a UPS also, we are having the battery and inverter. So once you are having the EV in your vehicle, so if your vehicle is connected to that network, then you can say when the power goes off, then you can able to discharge your battery from the vehicle and you can able to power up your home. So even you can say your EV can work as a UPS, right? So this for a home. At the same time, if you are saying the commercial buildings, so just in your apartment, just you can aggregate all the EVs and you can able to supply that common loads. So that's what now people are talking about V2X. So that also available. So that's what we can say. If this and all will happen only by having the smart chargers. So if you're having the unidirectional chargers like now, you could not able to achieve these things. So just we should have the bidirectional chargers to achieve this V2X. So when we talk about this V2X, we are having a lot of benefits. Even we can say that if you're having the EV, you can able to participate in that market by aggregating that batteries in the EVs. At the same time, you can able to reduce the peak power demand. Suppose during the peak demand, you can say the price is higher. So that time you can discharge your vehicle and you can get the higher cost. So that time just we can able to reduce the peak demand. So that's what people earlier now know. We have studied that valley filling, peak saving. So those and all it's happening by aggregating all the TVs into the system. At the same time, we can able to help your other EVs, right? So that also is possible. And again, is the same V2X kind of concept, right? So here, because of aggregating these EVs and supplying to the grid, we can able to enhance that stability of the grid as well as enhance that reliability, and we can give the ancillary services by aggregating all these EVs into the system, right? So even integration of the renewables also it's very easier. Earlier, when you are integrating that renewables, you have to install that energy storage systems to mitigate this intermittency of these resources. But once you aggregate the batteries of the TV, that also can be helpful to mitigate this intermittency of this renewable energy sources, right? So here, when next level, if you talk about home energy management system, so in a home, we can say that application of IoT is realized in a home 100%. The reason is because of this home energy management only, this IoT getting popular, because we can able to integrate all these devices into the network easily, as compared to the industries and industries, we can say. Even the commercial buildings also, we can able to integrate it. So once you can connect all your devices into the networks, then you can able to you can have the control over every devices, and that not only the control over the devices, at the same time you can collect the data, and that data you are sending to the cloud, and you can able to do the lot of data analytics, and it can open up a lot of business opportunities. So that's what we can say. The IoT plays a huge role in the home energy management system. Here, when we come into that different layers of network, so here that layers of the network for home energy management system is entirely different from that computer science networks, but it's I mean, network layers are similar, but where we are implementing the security and integrating these devices, whether it's in a presentation layer or in management layer, at the same time that communication data layer where we are locating it. So that's what, just in the communication we can do these things. At the same time, here, the main aim of that home energy management system is, one is to save the energy. That means to manage that loads. At the same time, to monitoring as well as logging the data. So remote monitoring also it's possible, because all the devices are connected to the network. We can able to control over every devices in the system. So at the same time, in the consumer side, we can able to give the recommendation for that energy saving. So suppose if your electricity price is higher, then you can get that notification that, so your some of the unwanted loads might be there. So you can make it as a automate off, or you can say that we can switch off the devices by getting that notification. So as well as scheduling also it's easier. So by doing the scheduling, you can able to reduce the electricity cost, right? So these are all happening in that consumer side. That means in the load side of that smart grid. So now when we come to the renewable side, that's a distributed generation side. So here, when we talk about that distributed generation sources, whether wind or photovoltaic systems, so you must have that power electronic converters between your source and the grid. So here you can see that you are having the bidirectional converter or unidirectional converter. So mostly in that wind and photovoltaic system, that unidirectional converter is most sufficient if you're talking about the grid connected system. The reason is, so whatever the power you are generating, just you are going to feed into that network, right? So, but here where we are integrating the energy storage, so that also it's very much important. So based on that integration of the energy storage devices, you can decide whether you need that unidirectional converter or bidirectional converters. So if you talk about the microgrids, the bidirectional converters plays the huge role. If you're talking about only the grid connected system, then unidirectional converters are more than sufficient. So in this, if we talk about power electronic converters, that control techniques also is very much important. So just we have to give the pure, power supply or quality supply to that grid. So these controllers will take care of it. So that's what we are saying is the intelligent controllers. So by giving the set points, we can able to inject the power or drawing the power from the grid, whatever we can do by controlling the controllers. So here, just we can say, when we connect it to the grid, then in most of the paper, if you look at that grid connected system, whether it's a wind or photovoltaic systems, they will talk about independent control of real and reactive powers. So by keeping a one power as a constant, active power as a constant, then you can make that power factor's unity at the point of common coupling, right? Or you can say leading power factor or lagging power factor, is it possible? So we can say that your system is working as a synchronous condenser, right? Just we can, if you're making as a leading power factor and lagging power factor, we can say it's a synchronous generator, synchronous machines, right? So in that way, just we can able to achieve this independent control of active and reactive power. At the same time, we can able to meet out the grid codes. That's very much important, because once you are connecting to the grid, if any fault happen, then you have to inject the reactive power to the grid to bring back that voltage back. So as per grid code, just we are having the timings. So based on the timings, just we have to follow the grid code. So for that, the power electronic converters plays a huge role in the renewable energy side. So when you come into the wind turbines, so especially on that wind energy converter system, so here we can see that this we can say is a diagram of wind energy converter system, grid connected system. So here in the generator side, you are having the rotor. So in the rotor, you can able to control the rotor, right? So by changing the tilt angle of the blades, you can able to control the rotor. So here we can able to control the frequency and generator. And here we are having the power converters. So by using the power converters, we can able to connect that energy storage into the system, and we can able to make that reliable power supply to the grid. So in the grid side, people will look into that independent control of active and reactive power, as well as just we can say so frequency and voltage stabilization. That's what just we are going that independent control of P and Q. So here we can say why we are need that fast response means because of power electronic converters, we can able to achieve that very good quick response, P reference. That means P response means it's an active power injection that we can able to do it. So here, before going to that for wind energy converter system, just I need to give some basics of that wind energy converter system. So once you understand this basics of wind turbines, then that will be very easy for you to select that generator or power electronic converters. So here, if you look at that wind turbine, the wind turbine power output is mechanical power output we are getting. So that is half rho AV cube CP. So here the rho is the air density and A is the area of the wind turbine. So here the area of the wind turbine depending upon the length of the blade. So if you are changing the length of the blades, the area can be varied. So if you are increasing, an area will be increased. So if area goes higher, then the power output from the turbine also will be increased. So here the next is CP, that is a power coefficient. So that power coefficient depending upon the tip speed ratio as well as the turbine speed. So by operating the turbine at the optimum speed, we can able to get this CP at the maximum power coefficient, so that we can say that maximum power can be drawing from the wind turbine. So here we can say that another parameter is wind velocity. So here we can say this CP will be fixed and rho will be depending upon the area, A will be depending upon the length of the blade. So now we can say the power output of the turbine is directly proportional to the cube of the wind velocity, we can say. So if you are changing a 1 meter per second in the speed, wind velocity, there is a huge change in the power output of the turbine. So that's what we can say for different wind turbine speeds. Just we are having the power output curve. So even if you look at that, for fixing the one wind velocity, we can say wind velocity in per unit, and all units are in per unit if we can take. So here, if your wind velocity is 0.5 meter per second, so this is the curve, then 0.6 meter per second, this is a curve, then 0.7, this one, 0.8, this one, 0.9, this one. For example, just I can consider for one wind velocity. So that is 0.9 per unit, I can say. So in this wind velocity, you can able to operate your turbine at the speed of 1.1, or you can able to operate at the 0.9, or you can able to operate the turbine at this point, 0.7, or any point in this curve. So if I'm operating at that wind turbine speed at 1.1, my turbine output is 0.6 per unit. If I'm operating at that 0.9 per unit, my turbine output is 0.9. So instead of that, if I'm operating at 0.7, so my turbine output is 0.6. So which point I prefer to operate? I prefer to operate at this point, because in this point only I'm getting a maximum power from the wind turbine. So if you're operating at this 0.9 per unit, then my power output from the wind turbine also will be maximum. So that during the 0.9 per unit wind velocity, then I will force my turbine to rotate at 0.9 per unit. So if I'm rotating my turbine at 0.9 per unit, then my turbine output power is 0.7, right? So that's what, just we have to control the speed of the turbine to achieve this point, operating point. So for that, you have to control the speed of the turbine by measuring the wind velocity. So if I say 0.9 per unit wind velocity, so that time I have to operate my turbine at the speed of 0.9. So for that, I have to control the speed of the turbine. So I have to fix the turbine speed at 0.9. So then only I'll get the maximum power from the turbine, right? So here in a real time, the wind velocity will keep on change. So for example, if my wind velocity is 1.1 per unit, so that time I have to operate my turbine at 1 per unit speed, right? So in that way, we have to keep on change the turbine speed depending upon the wind velocity, So here in this, you can join all these maximum power points, then just we'll get the power curve of the wind turbine. So whenever we are going for that wind turbine manufacturer, we'll get this power curve. So this is one of the very important power curve. So in this power curve, we are having the different operating regions. So here, cut-in speed, after cut-in speed only, you have to allow the turbine to rotate. So if you are allowing the turbine below cut-in speed, so whatever the power generating, it's going for the loss. So that's what we'll always operate the wind turbine above cut-in speed. So typically, we can say 3 meter per second to 5 meter per second. Sorry. So here, we can say that from cut-in speed to rated speed, we are implementing the maximum power point tracking. So we can look at that. These are the points we have to track. I mean, by looking at the wind velocity, we have to change the speed of the wind turbine. So that in this region, we'll implement the maximum power point tracking algorithm. So that time, we'll use the generator control. The reason is we'll not use the mechanical control, because in the wind turbine, we are having the blades having the high inertia. So the response is very slower. So that's what we'll use the generator control, because your turbine is connected to the machine through the gearbox. So once the generator speed is changed, then your turbine speed also will change, right? So here, that's what just we'll go with the generator control, right? So that's what the power electronics plays a huge role. So how will you control the generator? By using the power electronic converter. So that's what, without power electronic converter, we could not be able to operate that wind turbine in this maximum power point tracking region. So these are the region. Up to this, we will implement the maximum power point tracking algorithm. So after rated speed, we can say wind velocity is 12 meters per second to 15 meters per second. Then we can say whatever the wind velocity, your output power is constant from the turbine. So that time your turbine should not go higher speed. So in that case, we can say we should not go the turbine at the higher speed. So for that case, we'll apply the pitch control. So by changing the tilt angle of the blades, we can able to change the speed of the turbine, right? So up to 22 to 25 meter per second, we'll allow the turbine to operate. So after that, we'll not allow the turbine to operate because we could not able to control the speed of the turbine. So that time we'll stall the turbine, right? So this is the different operating region. So only in this region, we'll implement the maximum power point tracking by using the generator control. That means if you are saying that to control the speed of the generator, we need the power electronic converters. Now you can understand that the importance of the power electronic converters in the wind energy conversion system. So when we come into the wind energy conversion system, you can classify as grid connected system, standalone system, whatever the power you are generating and you are feeding into the grid. And here you will implement, even if you take any paper, research paper on that wind or photovoltaic systems on grid connected topologies, they will talk about various power electronic converter topologies, or they may talk about various control strategies on the grid connected system, right? Or in a few people, they were working on the grid code compliances, and some people, they may work on grid synchronization, independent control of real and reactive power. So everything will come under the grid connected system in the research side. In the standalone system, so you know that standalone systems for supplying the load as a consumer, I will expect the constant voltage and constant frequency. So in this also, they will implement various maximum power point tracking algorithms, converter topologies, and the sizing of the system that and all come into the standalone system side. So these are the main components of that wind energy conversion system. So here, if you look at that, gearbox and power converters are optional. Nowadays, people are trying to eliminate the gearbox from the wind turbine to reduce the cost. The power converters, if you see that, earlier they haven't used any power converter topologies, but now for implementing the maximum power point tracking, they will interfacing the power electronic converters between the generator and the grid. And here, if you look at that, whether if you are having the power converters, you can change the generator also. So now, if you want to eliminate this gearbox, you can go with that permanent magnet synchronous generators, so that at low speed also, it can able to generate the power at variable voltage and variable frequency. So that we can convert into DC, then DC into fixed AC can convert, and you can feed into the grid. So that's what the power converters also plays a huge role when you are talking about the direct driven wind turbines. That means without gearbox, we can say that turbines are direct driven wind turbines. So here in a fixed speed generators, we will not use that synchronous generator as a synchronous machine as a generator. The reason is just we need two types of power supplies. At the same time, just we need the synchronization for the synchronous machines. So that itself is a huge task. And the advantage is it will operate at leading and lagging power factor operation. But here, for connecting to the grid, you have to operate at a constant speed. From the wind turbine, you cannot able to operate that machine at a constant speed. So that's what we will not use the synchronous machines for the wind turbine applications. The best candidate is screw cage machines. So here we can say the screw cage machines are rugged construction. So you need not require much maintenance for that screw cage machines. So this will operate as a generator if you are rotating the machine above synchronous speed, right? So if I'm saying it's a 50 hertz power supply, 4-pole machine, then if I'm rotating above 1500 RPM, then we can able to inject the power into the grid. So we can say this is a single fed machine. The reason is the rotor is short circuited and the stator is, we are having the stator winding, so that stator windings are connected to the grid. So that's what we are saying is a single fed machine. But if you are talking about synchronous machines, you are having the field and armature is again it's a double fed machine. Or if you talk about the slip ring machines, you are having the rotor windings and stator windings. So that also is a doubly fed machines. But this full gauge machine is a single fed machine. So here, one of the disadvantages, whether this full gauge machine act as a motor or generator always draws the reactive power from the grid. So once you are drawing the reactive power from the grid, then at the point of common coupling, your power factor is lagging. So for lagging power factor, just we'll use the capacitor banks. So this capacitor banks will provide the magnetizing current to the machine. So at the point of common coupling, you can able to enhance the power factor. So when we come to the variable speed wind turbines, so in the variable speed wind turbines, we are having the 4 topologies. So in this, if you look at that, we are using in 2 topologies. One is a permanent magnet synchronous generator based wind turbines, and another one is a spool cage induction generator based wind turbines. So here in the permanent magnet synchronous generator, we can say that whatever the power we are generating here, we are channeling that power to the grid through the power electronic converter. So if I'm generating, if I say it's a 5 megawatt machine, all 5 megawatt of the power we are transferring to the grid through the converters. So this converter ratings also equal to the machine rating. So that's what we are saying, that full rated power electronic converter. So this converter ratings are equal to the machine rating. So here you are having the machine side converter, and here you are having the grid side converter. So the machine side converter can be used for implementing the maximum power point tracking. That means by controlling this PWM rectifier, you can able to control the speed of the machine. So here this PWM inverter will take care of maintaining the constant DC link voltage. At the same time, for independent control of active and reactive power in the grid as per the grid codes, right? Then here, if you want to synchronize into the grid, then we are having the PLL in the control strategy of this grid side inverter. So that PLL will be helpful for synchronization of this wind turbine to the grid. So, but of course, we are having the control strategies, as well as we are having how many switches. So here we are having 6 switches. Here we are having the 6 power electronic switches. So totally we are having the 12 power electronic switches. So controlling is a little complex. In the spool cage machine also, that power converter ratings are equal to the machine rating, right? So here the magnetizing current required for this machine is drawing from the grid, right? So at the same time, we can say both are bidirectional converters. So if you are putting the diode bridge rectifier here, so this machine will not act as a generator, because the magnetizing current required for the machine is supplied by this converter. So once you put a diode bridge rectifier, there's a unidirectional converter, so you cannot able to supply the reactive power to the machine, right? So here, if you are putting the diode bridge rectifier, so if I want to make this spool cage machine as a generator, what I need to do? Anyone having any idea about it? Like earlier case? Here we are we are connecting the capacitor banks for providing the magnetizing current. So here, if you are putting the diode bridge rectifier here, then just we can connect the capacitor banks. So that capacitor banks will provide the magnetizing current to the machine to create the flux, right? So that's what if you are changing the topology, then just you have to add the capacitor banks. So here also the converter ratings are equal to the machine rating, because all the power generated by these generators should be passed through the converters. But here in that slip ring induction machine based generator topologies, if you look into it, so here the converter ratings are only 30%. The reason is we can say that only the slip power you are extracting from the rotor windings, right? So that's what we can maximum we can operate to the 20% slip, we can say. So only that power can be handled by these power electronic converters. So that's what in these 2 topologies, the power converter ratings are 30% of the machine rating. So now we'll go one by one. First, wound rotor induction generator. So in this, we are having the rotor resistance control method. So this generator will, this system will work as a generator above synchronous speed. So if you are saying it's a 50 hertz, you are having a 4-pole machine, then it will act as a generator above 1500 RPM, right? So above 1500 RPM, it will start to generate the power and can feed into the grid. So by varying here we are having the chopper we are having only single switch. By controlling the single switch, that means by changing the duty ratio of that chopper, we can able to vary the equivalent resistance at the rotor windings. So once you are varying the rotor winding resistance, that speed can be controlled. So that's what, when we talk about the state of art of the wind, they are having a partial control, right? So partial control means we can able to control above 1500 RPM by varying the rotor resistance, right? So here it's a very easy topology. The reason is we are having only one single switch in the chopper. So controlling that single switch is easier. So when we come into the W-fed induction generators, in the W-fed induction generators, we are having the bidirectional converters. So here in the bidirectional converters, we are having a back-to-back converters at the rotor side. So here, whatever the power you are extracting from that rotor, you are feeding back into the grid at the subsynchronous, at the supersynchronous generation. In a subsynchronous generation, if you want to make this machine as a generator, you will draw the power from the grid and you are injecting into the rotor at a slip frequency to make this machine as a generator at a subsynchronous speeds. So below 1500 RPM, you are having a 200 RPM range, and above 1500 RPM, 200. So 1300 to 1700 RPM, we can able to make this topology as a generator. So this will be called as a W-fed induction generator. So here we can able to make that machine as a generator below synchronous speed as well as above synchronous speed. So this is a general control of that wind turbine system. So here, when we come into the energy management perspective, so people will connect the energy storage system into the DC link, so that you can able to balance that power, as well as you can give the ancillary services to the grid. At the same time, for voltage and frequency stability also, it's possible by integrating the battery and storage or end storage devices into that. So when we come into the control aspect, so just we are getting a lot of input parameters from the system. We can say in the status side, currents, voltages, speed, wind velocity, and this side we are having a grid voltage, grid current, and from the grid voltage and grid current, we can able to estimate that power, real power and reactive power, and we are having that software filters. So everything we can able to implement in the control strategy. So that's what in which area you want to work. So you have to decide. Then you can decide this power converter topologies, and you can decide the function. So based on the function, you can able to operate it, right? So that's what we can say. Depending upon the area, you can. I mean, if you are working on the power system perspective, then you can take all the things and you can work on it. If you are working on the power electronic side, then only just you can concentrate on the various converter topologies as well as various control strategies on that converters. So, and implementation of the maximum power point tracking, you can able to do it. So if you are a system guy and if you want to integrate into the system and you have to check that grid codes and everything, then just you must have all these functional blocks. So that will be helpful for testing your system or testing your algorithm which you have developed. So here, from the existing one, just we have modified the topology, and we are saying that just we have implemented for energy saving perspective, and we can able to say is an energy efficient turbine. So in later cases, in the rotor resistance control method, if you look at it, earlier they have used the fixed resistance as well as whatever the power we are extracting from the rotor, that can be go as a heat in the resistor, fixed resistors. So, but here, if you look at that, just simply we have modified this. Instead of fixed resistance, we have put it as a variable resistance. Why we put a variable resistance means whatever the slip power you are extracting, that can be used for the space heating purpose. At the same time, if we are not having any space heating loads, that time instead of dissipating the power in the fixed resistors, what we have put is just we put a one simple switch and battery in the rotor side. So once there is no load, so if I say is a no load means resistance is higher. So if the resistance is higher, then your voltage will be higher than the battery voltage. So that time your switch is on, then whatever the power you are extracting, that can be fed into the battery. So here, once you are having the loads, we can say some space heating loads. So that time if your load increases, the resistance come down, right? So that time it will be short circuited. So if you can assume that there is a short circuit happen or the resistance is coming down, then your voltage will be lesser at this point as compared to this point. So that time this diode will be reverse biased, then it will open, your switch will be open. So that time your battery will not be discharged to the space heating load. So whatever the power you are extracting from the rotor, that can be used for the space heating applications, right? So then here that limitation is we do not have any kind of BMS for it. So if you're not having any BMS, then you cannot able to discharge this battery. So just you have to swap the battery. That's the only thing is a limitation of this work. But here the thing is that instead of wasting the heat, just we are saving to the battery. So that's what we are saying, that by varying the power electronic converter topologies into the system, we can have the very good energy management in the wind turbines, right? So that also it's possible. But for that, you have to develop the new power converter topologies. So how we can make the system energy efficient. So that's what just we got this idea and just we can implement it. On top of that power converter topologies, in that control strategy also, just we can implement speed sensorless algorithm for implementing the maximum power point tracking. At the same time, we can make our wind turbines as a dispatchable power supplies. So for that also, just we have developed that algorithm. So based on that set point, your system can work in the maximum power point tracking mode, or you can say in the constant dispatchable power mode. Constant dispatchable power mode means it will not operate in the MPPT. So MPPT means the maximum power point tracking, so that you can control the duty ratio of the chopper and you can able to vary the speed of the wind turbine. So that's the maximum power point tracking. So in the constant dispatchable mode means you are not having any control. So whatever the power demand from the grid, only that power you are sending to the grid. Then rest of the power can be coming as a slip power. That power can be stored in the battery, right? So that is a constant dispatchable mode. So that is very much required for implementing the grid codes into the system. So for that, just we made that wind turbine as a dispatchable power source, right? So these things is very common because we are having only single switch. So for controlling the single switch, then only one pulse is required. So just we can go with that generation of the duty ratio based on the error signal from these two control decision block. So these are the experimental setup which we have carried out in the bound rotor induction generators. And next, when we talk about that WFET induction machines, so just slightly we changed some of the topologies here. Here, when we talk about WFET induction generator, if you take any literature in the whether in IEEE or any journal, in the literature we are having a back-to-back converters. So in the back-to-back converters means during the subsynchronous generation, you are extracting the power from the grid and you are feeding into the grid at the slip frequency. So during the supersynchronous generation, you are extracting the power and you are converting into variable voltage, variable DC, then fixed converting to fixed AC, fixed voltage and fixed frequency, and you are feeding into the grid. So for drawing the current from the grid as well as supplying to the grid, we are having the grid side converter. So that's the purpose of the grid side converter. We thought that why we should not replace the grid side converter with the battery and the storage. So if you are integrating the battery storage here, then your battery storage will take care of this injection as well as feeding into the grid. So that's what, even if you are having the converter at the grid side, it will inject a lot of harmonics to the grid. So that's what just we have replaced this grid side converter, the battery and the storage. So by having the battery and the storage at that DC link, so during the subsynchronous generation, we can inject the power, slip power into the rotor by drawing the power from the battery. So during the super synchronous, just we can extract the power and we can charge the battery. So here you have to inject the power into the in a sleep frequency. That's very much important, right? So for that we have used the scalar control. So this is the first time just we propose the single inverter battery fed DFIG for the grid connected operation. So here we have eliminated this grid side converter. By eliminating this grid side converter, we can able to eliminate the power quality issues. So some notification is coming. Organizers, this meeting is being transcribed. Okay. All right. So here, that's what just we eliminated, and we put this battery and storage for the grid connected operation. The same topologies, I mean, if you're putting it, just we have to analyze the different operating modes. So that for that, we have to take care of the energy management. So based on that energy management, so just we can able to find the different operating modes with the whether wind is more, load is less, and wind is less.
In the given food,
I think some interruption from that audience. I think Dr. Geeta Mani.
Sir,
Please.
muted.
Oh, yeah, sure. Right. So here, if based on that wind power availability and the load, just we have to, based on the energy management, we have to identify the different modes of operation. Then here, the different modes of operation, the speed of that generator is different. So we can say that if your wind power is equal, then we can say it'll only just small power is required for charging the battery. Discharge. So that time just we can say the machine operate at the near synchronous speed. So in this case, wind power is less, your demand is higher. So that time your battery can discharge and can meet out that demand. So here, if you look at that, wind power is higher as compared to the desired power. So that time, that rest of the power you are using to charge the batteries. So that time, just your machine will operate at a super synchronous speed. So in this subsynchronous speed, this is a super synchronous speed. And here, if you are not having any wind power, but the demand is there. So that time you can make this machine as a rotate. I mean, you might have here that machine is a rotating transformer, right? So slip ring machine. So now you can arrest this rotor and you can make this machine as a transformer. So whatever the demand by the grid, that can be supplied by the battery and converter. So by arresting the rotor, if you're arresting the rotor, then your machine will act as a transformer, right? So that time we can say standstill condition. So that time you can able to meet out the demand. So now another case will come into the picture. If you're not having any demand, but you are having the wind power. So how we can able to use that wind energy. So in that case, what you can do is you can short circuit the stator, and in the rotor, just we can say by using this rotor side converter and the battery bank, we can able to make a virtual grid. So now it will act as a virtual grid to your rotor terminal. So here it's a stator is short circuited. So this will act as a normal induction generator. So that time, whatever the power you are generating from the wind, that can be stored in the battery. So instead of stalling the wind turbine, just we are short circuiting it and we are charging the battery, right? So that's what, by integrating the battery energy storage into the DC link, we can have this, liberty, we can say, right? So that's what we can say. We can say this mode 5 as a sorted stator indexing generator. Because you are short circuiting the stator and you are creating the virtual grid in the rotor and you are charging the battery, right? The same topology, you can use it for standalone supplies. So in the standalone supply also, you can able to maintain the constant voltage and frequency at the load side, irrespective of the change in the wind velocity and load. You can able to maintain the constant voltage and constant frequency, right? So these are the various topologies in the wind energy economic system with respect to energy management. So once you know energy management, that means meet out the supply and demand, you can able to identify the different modes of operation. So I'm having few slides of photovoltaic system, but due to of the time constraint, I'm skipping it. Thank you very much. I think I finished by 9:15 because I started at 8:50. So another 5 minutes we can go for question session. If you have any doubt or any clarification on this, please.
So now the session is open to audience. You can post the question to sir.
Someone is asking that instead of that battery, we can use the EV batteries. So EV batteries, you can directly cannot able to connect. As I said, you can aggregate it. So whenever you are not in use, you can aggregate this EVs, and based on that user requirement, suppose for another 1 hour, I'm planning to go out. So that time I cannot able to connect, I cannot able to discharge my batteries, right? So there are a lot of constraints come into the place, right? So in that way, you can aggregate it, and that aggregated energy storage, you can use it for energy, to supplement the physical energy storage in the microgrids. So in that way, straight away you need not to use, because the EV battery cost is higher as compared to lead acid batteries. So here for renewable application, lead acid batteries are more than sufficient. So we can use that lead acid batteries as a physical energy storage. So EV batteries, you can leverage that by using the technology, you can leverage and you can use it for microgrid applications, not for individual, systems. Yeah, if it was smart grid, yeah, again, you can use it. 100% you can use it. That means you can aggregate it. So once you aggregate, you will get some energy storage capacity. So that you can use it as a supplement. That means suppose in your microgrid, you require 100 megawatt hour. So if you can able to aggregate and you can get some storage capacity like 1 megawatt, not 1 megawatt, 10 megawatt hour, or 10 mega ampere hour. So just we can say 10% of the battery sizing we can able to reduce. That's what normally that aggregation we are doing it. So once you are having the smart chargers, you can able to aggregate, and that you can use it for assisting the physical battery storage. That we can do it in the smart grid. Exactly. So Mr. Arvind Kumar is asking about in cyber attacks, whether the current technology is good or not. So in a cyber attacks, if you are establishing the communication protocols, so in that network side, just we have to work on that, cyber security and all. So of course, in the smart grid, there is a cyber attack or malware attacks that will have the huge impact on the grid system. So just we need to go with that cybersecurity measures in the smart grid. Because once you are establishing the communicate, always the intruder enter into that network and can do some unwanted things. Maybe that can lead to the blackouts also. So for that that's what one of the even most of the people, they are working on the cyber security in a power system. So cyber security in a power system means it's a cyber security in the smart grid. So whenever you are enhancing your communication among the various devices, then there is a chance to get attacks. So for that, we need to go with that security, network security. Yeah, of course. Another person asked, can we get real-time data, real-time smart grid data set for any attack detection? Actually, I'm not working on that cyber security. So if you are really interested to know that cyber security, actually, I'm planning to have some short-term course on January 6 to 11. That short-term course is by MMTC, Madan Mohan Malviya Teacher Training Institute. So that might be useful for your, CAS promotions and all. Just you can refer the website or UGC site. You can get to know that short-term course details. In that, few people, one of my friend working in SUTD, so he will talk about cyber security and digital twin in smart grid system. Another person asking about, shall I go for MATLAB or Python for this? So here, suppose if you are planning to work on power electronics or power electronic converters, then you can go with the MATLAB or PSIM. If you are planning to work on data side, that means system level modeling, then Python is good one. Now, even one of my research scholars also working, not only, two scholars, they are working on Python for writing the code for optimization and modeling of the system. So you can try with the Python. Python is open source, so we can go ahead with that. How to get a data, I mean, out of this malware attack, that's what I told you. One of my friends going to talk about cybersecurity in smart grid on January. So I'll pass that short-term course details to the coordinator of this program. You can get the information from me. Another guy is asking MATLAB only we are using for simulation. Now there are models, but the blocks are not that much understandable. Is it possible to give some guidance and real-time data? That is difficult. How we can get that? I don't know for what system exactly you are asking about. Of course, whatever that models is available, they have modeled that system with the constraints. So just we have to understand for what constraints they have modeled. Suppose if you are planning to if some persons are working on the power electronic converters, that model you cannot use it for system level modeling, So in that you have to conditions, you have to check it and you have to remodel it. That's the only thing. Smart grid, there is no smart grid simulation. Actually, when we talk about the smart grid simulation, people, they are working on that security issues. Thus, we can emulate that various smart meters and various devices emulate, and you can collect the data. And even if you want some data, you can refer NREL. So NREL people, they are having some data, so you can refer NREL. So the NREL US lab. So I type it that NREL, or you can. NREL website. You can refer this NREL, so we'll get the data. Another person, my doubt is, as an electrical engineering scholar, shall we use Python cases? Yeah, you can use it, Python. You can use any tool. There is no necessary that you have to stick with the tool. Again, this MATLAB and PSIM and all, you are buying and you are using it. So there is no necessity that you have to use. Even if you have any open source platforms, you can use it. Even Python, you can use it for writing the code, plotting the graph, even plotting the figures and all, it's very easy. So once you learn, you can, in thesis writing, you can say
Good
it.
evening.
There is no issue.
Yeah, good evening, sir. So myself only have asked that doubt. If we publish the paper using the MATLAB by getting that output.
No, actually, no. Suppose if you are working on that system level or on the technical side, there is no compulsion that we have to use MATLAB or PSIM. Nowhere they will mention.
No,
But the
my
thing
doubt
is,
is if already we published the paper using the MATLAB and we got the output, and if we are using another platform like Python in that thesis, means if any problem will be occur in that evaluation or.
No, there is not at all a problem, because if you are having that license, then we can say that we have implemented using a MATLAB. So without license, if you are saying that we are using a MATLAB, then there is a conflict of interest, right? So, but Python is a open source.
Okay, sir.
So we can say just we have even a Python, we can write a lot of programs as well as we can plot the curves, everything we can do it in the Python. We can do it, we can use it.
Okay, sir. Thank you.
Yeah, thank you. And another person asking, how does power electronic converters useful for hydrogen fuels? Of course, now the hydrogen also is one of the technology in we can say is the talk of the town. The reason is earlier they have produced the hydrogen by using the electrolyzers, right? So that means just we can use the electricity. That electricity is given to the electrolyzers. That electrolyzers can generate the hydrogen. So that's what, if you want to produce the hydrogen, then electrolyzers are required. For that electrolyzers, you need the power converters. At the same time, now people are talking about the green hydrogen, right? So how we are saying is that green hydrogen means earlier they have used the hydrogen from the grid. They used the electricity from the grid and they have produced the hydrogen. But now here in 2005 and 2000, you might hear that in Tamil Nadu, that too in the Coimbatore region. Actually, I'm from Coimbatore only. So in the Coimbatore region, they have a lot of wind turbines, but they do not have the sufficient infrastructure to feed the power into the grid. So that time, what they have done, off of the wind turbines, they stopped only, they have operated only off of the turbines in the month of May, June, July, August. So instead of stalling the wind turbine, that just we can operate the turbine, generate the power, that power, you can use it for produce the hydrogen. So that hydrogen, that excess power you are using for producing the hydrogen, so that hydrogen will be called as the green hydrogen. So now even the government also coming up with a lot of subsidies for this. Even that Reliance and some of the players also, they come into that hydrogen economy, because the hydrogen is used in that fertilizers, chemical industries, steel industries. So huge demand for the hydrogen. So in that, they're using a power converter. So even that hydrogen, again, you can use it for producing the electricity. That is a fuel cell. Even in a EV also, there is two types. One is battery operated vehicle, and another one is fuel cell operated vehicles. So that also is electric vehicle. So instead of battery storage, you are having the fuel cell, hydrogen storage tank and fuel cell. So that by using that, you can generating the electricity and you are driving your vehicle. So that we can say for hydrogen fuels as well as for fuel cell technology, you require the power electronic converter. So the power electronic converters plays a huge role in that also. So shall we get the data from the MathWorks? I do not have specific idea about the MathWorks. So, but data set, if you're talking about that data set, you can get it from the NREL. I don't know which data you are talking about, Muthupriya. Just we can MATLAB. I don't know about the specific data about MATLAB. So whether you are talking about which data, I don't know.
Sir, it's a data set, sir.
Which
through
data
that
set?
Yeah. So in order to work.
So data set. Suppose if you are working on that PV or wind, that estimation, wind velocity estimation or radiance estimation. For that, we can get that data from the NREL. So I don't know which data she is asking about in the MATLAB, MathWorks.
She is asking about that cyber attacks data, sir. So since we
Cyber
are
attack data, no, that and all not me. They have emulated. So some of the labs, they are having the microgrid. So with that, they have emulated that data. So there is no standard data set as like image processing or signal processing guy. So based on the system, no, we'll collect the data. We are not having any specific data like that. Even we are not having any smart grid up to now. So smart grid is not a new thing. It's enhancing the feature of the existing grid.
okay, sir.
Yeah, thank you.
Thank you, sir. Vijay Kumar, sir.
Sir, thank you.
Sir, from many of the faculty members attending, they are asking for this PPT, sir.
Yeah, sure, sir. It's my pleasure to share.
Okay, sir. We will be sharing it with all the participants.
Yeah, sure, sir. Sure.
Thank you, sir. It was highly informative and interactive. Post of your presentation, the participants were opening up with their questions. Thank you. Even during late evening hours, it was.
Yeah. It's really it's a fantastic interactive session. That's what just I'm getting a lot of messages. Happy to see that. So if you are having any questions or doubts, let them mail me. So I'll try to answer. Or if they require my number, just we can share it. Let them write it in WhatsApp. So I'll try to answer. Thank you.
Thank you.
Thank you very much. Thank you all.
Thank you. So participants, tomorrow session is from 6 p.m. So we'll be sharing the same link. You can join through the same link, and please do complete the feedback for both session 1 and session 2. So it will be available till 10 a.m. tomorrow morning. Thank you all. Good night.
Oh,